But it should be working now?
Yeah. Sorry?
So, but we're not seeing the slides. Yeah.
Oh.
Okay, so Yutong will start the theory session. Please go ahead. Oh,
Okay.
I see.
Cool. Thanks everybody for being here. I'm Maxine Xin from UT Austin, and today I'll be talking about TechMiner, a tool that we built to do automated discovery of tactic libraries for interact theorem proving. So to get us started, I assume everyone here is relatively familiar with the notion of interact theorem provers, ITPs. So there are a variety of ITPs being invented in the past decades, and they are widely used across the different domains, ranging from software and hardware verification, mathematics, cryptography, and many others. So I hope we all agree on sort of how important ITPs are. So let's talk more about them. One very important thing is how do we write proofs in them, right? And as I'm sure many of you here already know, the core building blocks in ITPs are tactics. So a tactic can be seen as an action we can make to do a one-step transformation to the proof state. For example, we can say introduce a variable to the context, or to rewrite the goal using some lemmas. And then we can use these tactics to gradually transform and simplify our proof goals until all the proof obligations are discharged. So great, these tactics are quite powerful. But unfortunately, most of these tactics, one tactic can only make a very small step transformation. So when the theorem gets really complex, the proof can get very low level and very verbose, so it becomes very hard to read. So to address this problem, many people write their own domain-specific custom tactics that they can use to make proofs more readable, more concise, and more reusable. And precisely because of that, people routinely write such custom tactics and package them into reusable libraries such as mathlib in Lean for mathematical proofs, or flock library in Coq for floating points. So this brings us to our central question, which is, wouldn't it be really nice if we can automatically learn such tactic libraries? In my opinion, this has a few benefits. So first, we can discover common proof patterns and motifs. And then we can use these patterns or abstractions to help with proof automation. As the abstractions that enable larger transformations can reduce the proof search space by a lot. Also, we can use them to facilitate a form of lifelong learning where we can continuously enrich the prover with new tactics and make the system steadily more capable over time. So in order to achieve all these really nice things listed here, we created a tool called TechMiner, which can automatically discover tactics from a given proof corpus, which means a set of proofs. So specifically, TechMiner takes a proof corpus and would output a tactic library that maximally compress the proof corpus. Furthermore, TechMiner can also be used to refactor these existing proofs using the extracted tactic library. Okay, so now we have a big picture on what TechMiner does and how it works. Let's actually break it down to talk about how we achieve the tasks. So for the remaining of the talk, I'm going to first talk about how to refactor proofs in a principled way, and then I'll be talking about how to detect common patterns that can be extracted as tactics and packaged into libraries. So let's first talk about the proof refactoring procedure. So the problem we're trying to solve here is given a custom tactic and a proof that can be refactored by the tactic. How do we exactly detect this and actually replace the corresponding proof text with the custom tactic? So one might think here, how about we just do it syntactically, right? So what that means is just given a custom tactic containing a sequence of atomic tactics in the tactic body, we can search if the same sequence of atomic tactics exists in the proof text modulo the tactic arguments. And if that exists, we can try to unify the custom tactic with the corresponding proof section by searching for the correct argument bindings. And if such search exists, then we can replace the proof texts with the custom tactic with the correct argument binding. However, TechMiner here doesn't necessarily agree with this approach, as we think this approach is too brittle and would actually miss many refactoring opportunities. For example, here's a counterexample. We can see that all the atomic tactics appearing in the body of the custom tactics actually are present in the proof below. But the problem is they are disconnected. We can see the yellow parts are disconnected, the green parts are disconnected. So when this happens, the previous syntactic approach would actually fail. So this poses our first challenge. How can we capture beyond just the brittle syntactic relationships? So basically, we need a different refactoring approach. So for this purpose, we introduce tactic dependency graph, TDGs, which are intended to capture the deeper semantics, the logical dependencies among tactics. And now I'll explain what its constructs are. So here, a node represents a tactic application. A tactic node would have its formal input and formal output decided by Rock's built-in semantics. And here, an edge would represent the dependencies between tactic applications. More specifically, an edge from tactic A to B, labeled from X, Y, indicates that the formal output X of A becomes the formal input Y of B. So yeah, because the TDGs can represent much more beyond just syntactic relationships, one TDG can actually represent very different proofs. For example, I have two proofs here which have the exact same atomic tactics but in very different orders. But both of them can actually be represented by the same TDG here. Okay, so clearly, clearly I hope we all understand what TDGs are and how they work right now. So let's actually talk about how do we refactor the proofs using our TDGs. It's actually pretty straightforward. So given a Rock scripts, we just first convert it into the TDG representation, of course, and then we find isomorphic subgraphs in the proof TDG that corresponds to the tactic TDG, which are the highlighted parts over there. And then we, to actually do the refactoring, we just create two new nodes representing the custom tactics. And then we replace the corresponding subgraphs with the newly created node while maintaining the incoming and outgoing dependencies. OK, cool. So and then we can just use topological source to convert the refactored TDGs into the Rock scripts. So now that we understand how the refactoring procedure works, the tactic learning procedure actually follows pretty intuitively. So given a proof corpus, we just we just try to find their common isomorphic subgraphs, and that will give us our extracted tactic. So I know some of you might be thinking okay, this is conceptually straightforward, but how about in execution, since as we all know, finding isomorphic subgraphs is hard. And so for that, we used a graph enumeration technique, where the enumeration is guided by its input and also enhanced with some pruning techniques, which made the enumeration computationally feasible. I'm not going to talk about the details here, but please refer to our paper if you're interested. OK, so now we have understand both of the procedure. Let's actually chain them together to get the big picture. So given a set of proof corpus, we will first just extract the tactic that maximizes our defined objective, here the compression ratio, and then we can refactor the proofs using this extracted tactic. And then we can repeat this procedure until no further tactics can be found, which means no further common subgraphs can be found. And the output will be our tactic library. And to understand how our work did, we want to know how well can TechMiner extract libraries from existing proofs, and if learned tactics help with proof automation. And since this is time limit, I'm just going to quickly say like we compare with the syntactic approach that a tool called Piano we talked about earlier, and we have like gathered proofs from these different domains. We compared, we have two results for the first research question. The first one is on the statistics of the tactics we extracted. We can see that TechMiner learns 3 times of the tactic learned by Piano and are much more frequently used as well. And they also achieve much higher compression rate. So our first conclusion is that TechMiner learns 3 times tactic compared to Piano, and with the baseline, and reduces the corpus size by 26%, while Piano only does it by 9%. Okay, and our secondary experiment is on proof automation. So we want to see how our tactics help improve with the proof automation results. For the proof automation tool, we chose Copra, which is one of the state-of-art proof automation tool that it's LLM assisted with compiler feedback. And in this experiment, we compare the proof automation results between the out-of-box Copra with the Copra with Piano and TechMiner extracted tactics. And what that means is just like we give Copra the information about the custom tactics it can use and how to use them. Okay, cool. Yeah, if you have any questions, and Maxine, feel free to talk to me after the talk.
Like the generated names for the generated tactics, do they matter in terms of how the LLM processes them?
I need to speak in the mic.
Yeah. You can speak into the microphone.
Okay.
Yeah.
It was not happening.
Yeah. I just turned it on.
Yeah, okay, thank you very much.
Okay, so yeah, thanks for the questions. Next talk, is it working now?
Yes.
Okay, great. So please go ahead.
Yes. Where's the mic?
Use this one.
No.
Okay, don't use this one.
Testing. All right, everyone, so I'm Ashley, and I'd like to talk to you about a new choreographic programming language that I developed together with my advisor, Ethan Cicchetti, and our collaborator, Andrew Hirsch. Both Andrew and I will be here to answer any questions you might have offline after my talk. So we're interested in concurrent programming languages, and if you've ever tried building a concurrent system that doesn't immediately break, you might know just how hard that can be. In concurrent programming, you typically have a program for each process in your system, like Alice or Bob. To ensure that nothing goes wrong, you need to both ensure that Alice and Bob's programs don't have any errors, and that all communication between those two processes goes as expected, which means that no one sends an unexpected message, and no one waits for a message which never arrives. Well, for two processes, this may not seem bad. As you add more and more processes to your system, you have to add a new program for each of those processes and verify the communication between all pairs of processes. And this just makes our developers' heads spin. She can't manage all these programs and all this communication that happens. So concurrent programming is hard. And this isn't even to mention the other sources of bugs in concurrent programs, like data races. But fortunately, there is a solution. And that solution is choreographies. So choreographies make concurrent programming easy. So choreographic programming is an emerging paradigm for concurrent programming that seeks to simplify concurrent software development while yielding strong formal guarantees. So in the choreographic paradigm, you write a single top-level program called a choreography that specifies the actions of all participants in the system, regardless of how many participants there are. We then have a compilation procedure called endpoint projection, which extracts out the actions of every single participant in that system, yielding a system of programs that can be then executed concurrently. So besides simplifying that software development, choreographies also have a property called deadlock freedom by design, which means that if you can prove that the choreography is safe, which is typically done by means of a lightweight type system, then you can transfer this guarantee to the concurrent system created by endpoint projection. And this concurrent system will be deadlock-free, meaning there will be no deadlocks in the system, and it won't crash for that reason or any other reason. So to illustrate some details about how choreographies work and to motivate our work, I'd like to talk about how a programmer can implement a system in which Alice buys a book in collaboration with a few other processes. So the book that Alice wants to buy is called Death in Venice by Thomas Mann. So to determine which of Bob and Charlie she wants to buy this book from, she's first going to tell Marty which book she wants to buy. Marty stores a list of all the prices and availability of these books, and Marty will send this data back to Alice. So we could let Alice choose to decide her vendor based on any criteria we want, such as preferring a local business. But for simplicity, let's just have her choose the cheapest vendor, which in this case is Charlie. So importantly, this procedure was dynamic. Alice only learned this information at runtime. So if there's a different execution environment of this program where the prices might have been different, Alice's decision might differ. And this feature is a key, this ability is a key feature of our work. So then lastly, to complete this transaction, Alice sends the name of the book as well as the purchase price to the chosen vendor, Charlie, and Charlie can send back the book, and then everyone is satisfied. So as I mentioned, the key component of that process that we want to work on in our work is to enable choreographies to dynamically select processes. So prior work technically has the ability to implement this functionality, but it was never a major focus of prior work, so it's up to the programmer to implement this functionality in an ad hoc manner using other features. In our work, in contrast, we enable dynamic process selection in a programmer-friendly manner by adding new language features, which increase modularity and decrease the chance for errors. So let me show you how this book buying example can be written using prior work. So the nice thing about choreographies is they look very close to normal single-threaded applications, except you sometimes have some extra information to denote which of the processes in your system will perform each action. So here we allow Alice to choose a vendor by prefixing the name of this function called chooseVendor with an A followed by a period. So this function returns a string representing the chosen vendor. So we're going to branch based on that value. So in this first branch, we handle when Bob is chosen. The code that this case executes calls this transaction function with the arguments Alice and Bob. This transaction function is process polymorphic. It abstracts over the processes in this function, which is a feature of prior work. This means we only need to write this transaction function once and just call it using different arguments in each branch. But if we want to add another vendor to our system, say Dan or Aaron, we need to add another branch to our case expression and change the arguments to this transaction function. 4 vendors isn't super realistic. We have to add a lot more vendors for a more realistic scenario. We have to add another case of our case expression for each of these vendors. But this isn't very modular. This isn't a very good idea, because if you zoom in here, you can see there's actually a mistake. When Oliver was the selected vendor, the sale mistakenly went to James. And this isn't a very good thing to happen. In fact, this is a real mistake I made when typing up this example. So writing so many cases is very clearly unsustainable and can lead to programmer error. And this, again, makes our developers head spin. So how can we fix these problems? So our main observation is that if we can treat the name of the selected vendor like any other value and bind it to a variable, then our programmer can write this book vendor example in a simple and modular manner. So that is, our solution specifically is to treat these process names as first-class values. So just like before in this code, Alice first dynamically selects a process by calling this choose_vendor function, producing this time a first-class process name. However, in our new language, there's no need to branch based on the value that selected vendor takes. And this is because of a key contribution of our new language called a type let expression. So this is a new form of let expression, which binds that vendor to the process variable L. So the body of this let expression is nearly identical to in the previous implementation, but we're replacing the specific vendor, like Bob or Charlie, with that process variable L. So this both eliminates the duplicate code, which appeared in the branches of the previous example, and allows the programmer to reduce the chance for errors by writing it once and for all, regardless of how many vendors are in the system. But you say, this is a let expression. This is kind of simple. Are you really going to stand up here and tell us how let expressions work for the next 5 minutes? And that is kind of what I'm going to do, but it's not that easy. If this solution works, well, why didn't previous languages implement it? Well, it's not that they didn't know what let expressions are, didn't think to add in let expressions to their language. First-class process names are actually quite complicated. So let me show you how our language manages to safely implement this feature. So firstly, we need to be a bit careful about the sort of things in this program, because when Alice chooses this vendor, this is something like a string, an expression, but this process variable L is actually at the level of types. So to give this let expression a sensible semantics, we need to have a way to convert expressions into types. And we allow this in our language by letting the user configure the runtime to define this conversion function. Another subtle point is that if you ever see in programming languages an arrow pointing from expressions to types, you should immediately think of type dependency. And dependent types aren't necessarily bad, per se. They can just make your type system extremely complicated or even undecidable. So in our language, we would really like to avoid a type dependency whenever possible. So to see how we might unintentionally introduce dependent types, in this example, if the chosen vendor returns their street address, in one case, when Bob is chosen, that results in a string at B, or Bob. The other case, it results in a string at Charlie. So then what type should we assign to the entire let expression? Well, it depends on what value L resolves to. So our language solution to this is basically just to ignore this. We say this isn't allowed in a language. Well, we don't exactly ignore it. So to be more precise, what we say is that we look at the type of this expression where the variable L is in scope, look at the type of it, and say, if it depends on L, this is not allowed in our language. So this example is not allowed because a string at L clearly depends on L. So we don't allow such a let expression to type check in our language. In contrast, that earlier actual example of our book vendor returns a book at Alice, which does not depend on the chosen vendor L. So this entire let expression type checks in our language, and it produces a book at Alice. So by imposing this mild form of restriction on how this let expression can be used, we can completely avoid dependent types while still allowing forms of dynamic process selection. So another small problem that comes up in our language is called the knowledge of choice problem. And this involves a scenario where Alice selects a dynamic process, but Bob and Charlie don't necessarily know who was selected. Charlie doesn't know whether to wait for a message from Bob and from Alice, and neither does Bob. So in our language, we enforce that this message is sent to both Bob and Charlie, the relevant processes, before that transaction can occur. Once that information is conveyed to Bob and Charlie, the transaction can proceed as normal, where Alice will then send the message and money to Charlie, and Charlie will send back the book. If a different vendor was selected, the name of our language implies that we can quickly change the selected vendor from Charlie to Bob. So in conclusion, we developed a language called the Choreographic Quick Change Calculus, or Lambda QC. We added new first-class process names, as well as a type of let expression to handle those first-class process names. We used existing features from previous choreographic languages, like process polymorphism and multiply located values. We have an endpoint projection compilation procedure to compile these choreographic programs into one for each process in the system, and all of our work is verified in ROC. Thank you, and now I can take any questions.
Thank you. Unfortunately, we don't have time for questions, so please, the next speaker. Can you help with the mic? Can you help with the mic? Oh, okay. So you want this mic, right?
Yes.
Maybe first.
So hi everyone, my name is Ivana. I'm from the University of Technology in Vienna, and today I would like to talk about our paper, Divide and Conquer, a compositional approach to game theoretic security. So I would like to start by giving you a very high-level idea of what game theoretic security reasoning actually is. So in terms of blockchain technologies, what we mostly find in literature is work done on cryptographic security. And cryptographic security deals with questions like, for example, if I have a key, can a malicious person steal my key? So this is very important and absolutely necessary. However, it is not sufficient. In our setting, we would like to go a step further and also examine game theoretic security. As you will see in my presentation, in our setting, we deal with questions that analyze the economic incentives behind user behavior. So, as we will see, we will differentiate between honest and malicious players, and then we will analyze how users' behavior can make them gain some rewards or how it can cause penalties for other users. So how is it done? Well, blockchain protocols or any other protocols are first translated into game theoretic models, and on this slide we can see one small example. So this is called the market entry game, and as we can see, we have two players, M and E. M is a company that is about to enter the market, and E is a company that is already established. The players can take actions, so at the very beginning, M can either choose not to enter the market or enter the market. If M chooses not to enter the market, then we reach a leaf where we can find the utilities. So in this particular case, M will obtain a utility of 0, whereas the already established company will obtain the profit of the market P. In the other case, if M chooses to enter the market, then the already established company can either choose to ignore M, in which case they share the profit, or to start a price war, in which case they both lose some assets. It is important to mention that we have one honest behavior or intended scenario, and we always analyze a game theoretic model with respect to this honest behavior. Okay, so once you've seen the models, you might ask yourselves, what are the properties that we want to analyze and ensure that they hold? Well, for this, we differentiate between three types of behavior. We have the honest players, which always act according to the protocol. We have the rational players, which might deviate if they're incentivized to do so. That is, if a deviation promises them a strictly greater utility. And last but not least, we have the Byzantine players, which are potentially malicious and can deviate at any point just to harm other players. Having these three types of behavior in mind, we want to ensure that two properties hold. The first one being incentive compatibility, meaning that the honest behavior is always rational. And the second one, Byzantine fault tolerance, meaning that the honest players are never harmed. A protocol is defined to be game theoretically secure if and only if the honest behavior satisfies these two properties. So in a previous work, this has been automated as follows. On the left side, we have our game, constraints, honest behavior, and security properties, and all of these are translated into a large set of SMT constraints, which are then sent to the SMT solver. Depending on the output of the SMT solver, we can either decide that a protocol is secure, in which case we support strategy extraction, or that the protocol is not secure, in which case we can do precondition generation or counterexample generation. So this worked nice for protocols of smaller or medium sizes, but as you can imagine, protocols in real life can be quite large, which is why the previous approach encountered serious scalability issues. Motivated by this, we decided to employ compositionality techniques, and this is what our OOPSLA paper is about. So in our OOPSLA paper, in the compositional approach, we proceed with two levels of reasoning. The first level of reasoning is to stratify over the different players. So imagine we have a large protocol and we have our three players, Alice, Bob, and Eve. And what the previous approach did was basically analyze the model and try to find out whether the properties hold for all players at once. During our compositional approach, we proved that this is indeed equivalent to showing that the protocol is secure for the first player, Alice, and then also for Bob, and lastly, also for Eve. Each time we analyze a protocol from one fixed player, we assume that this fixed player is an honest player. Moreover, every time that we analyze a protocol for one fixed player, we perform a reasoning on a second level, which we call divide and conquer subtrees. I would like to illustrate how this works based on a very small example. So recall our market entry game that we had previously, and let's assume that the intended behavior is taking action E and then taking action I. Moreover, let's assume that we analyze this whole game in terms of Byzantine fault tolerance for the player M. So we proceed as follows. We ask ourselves two important questions. The first one is whether the player that has a turn is the same one that we analyze, and the second one, whether we are along the honest history. Depending on the answers of these questions, we then analyze only the subtrees that are relevant in the situation. So in this concrete situation, we see that we have M as a player, and this is the same player that we are analyzing the property for. So we have the assumption that this player is honest. Moreover, we are along the honest history, so there is an honest action available, which is why we know that this player will take this action, and then we can reduce the security of this larger game to the security of this smaller sub-game. So in this particular example, we do not need to analyze the subtree after n. And here it is just a leaf, but in practice it can be also a very large tree. Okay, so using these two levels of reasoning, our approach now looks as follows. We still have the same things on the left side, but now we have our player-wise iteration and the analysis on only the relevant subtrees, and we can still decide that a protocol is secure and extract strategies, this time in compositional manner, or we can decide that a protocol is not secure and generate preconditions and counter examples. So this gave us a sound and complete approach, which we also automated, and I would like to highlight some differences between the old framework, Checkmate, and the new one that we call Checkmate 2.0. So one interesting benchmark is tic-tac-toe, because for this benchmark, the old framework did not manage to terminate within 8 hours, so it was a timeout, and the new framework terminates in 42 seconds. In terms of SMT calls, the old framework had just one SMT call with one very big query which captured the aspect of the whole tree at one, whereas the new framework performs more than 10,000 SMT calls, however, with small, compact queries which do not impose a burden to the solver. In terms of evaluated nodes, the old framework analyzes, as expected, the whole tree and all nodes, whereas the new framework analyzes significantly less nodes. Another interesting benchmark is the three-player routing protocol from the Bitcoin Lightning Network. For this particular benchmark, the old framework needed about 50 minutes to extract all counterexamples, whereas the new framework does this in 5 minutes. Okay, so this gave us a nice scalability improvements. However, we wanted to push the compositionality aspect even further, and we introduced something that we call piecewise analysis. So for this one, imagine that we have a large real-world protocol, and as you can see here, we have some spots where we have S1, S3, S2, S3, S4, and so on. So these are, again, trees, or what we call subtrees, which are not on the image because they're pretty big and they did not even fit on the image. So let's look how they look. So this is S1, and it's, again, a pretty big tree. And what we now want to achieve is we want to analyze these subtrees independently. So we take S1, we want to analyze it independently as a standalone tree. We want to do this with S2, S3, S4, and all the other subtrees that we want to extract. And once we do that, we extract only the relevant information from the result. Once we have the extracted relevant information, we can plug this in the supertree whenever these subtrees occur, and we can discard the subtrees themselves. Now we can analyze the supertree where some results have already been pre-computed. This is especially beneficial for a benchmark called 4-player routing. So this is basically the same one as the 3-player routing from the Bitcoin Lightning Network with just one more additional player. And this approach is important for this benchmark because this benchmark has been generated and analyzed for the first time. So previously, the generation exceeded the allocated disk space, and since we were not even able to generate it, we were also not able to analyze it. We now proceed as follows. We still run our generation script. However, whenever we generate one particular unit of the protocol, called the unlocking phase, we generate this as a subtree. We send this to our framework Checkmate 2.0, and then it is analyzed, so that just this subtree, and Checkmate gives us the extracted relevant information, which we then plug in to the supertree. After we have the relevant information extracted from the result of the analysis, we can discard the subtree itself, and as you can imagine, the extracted information is way smaller than the subtree itself. We do this quite a lot of times, and in fact more than 1,400 times, and in this manner we are now able to generate this benchmark, and since it is relatively small, we can also analyze it quite quickly. Okay, so in conclusion, when it comes to game theoretic security, we've achieved significant scalability gains enabled by compositional reasoning, and we did this in several different ways. We had the player-dependent notions, which we referred to as level 1 reasoning. Then we had reasoning over subgames and analysis of only the relevant subtrees, which we referred to as level 2 reasoning. Then we saw that we had interleaved subgame and supergame reasoning, which was beneficial, especially for the 4-player routing. And last but not least, we now perform strategies and counterexamples generation in a compositional manner. Yes, so with that being said, thank you for your attention, and I'm looking forward to your questions. Okay.
Hello,
Okay.
hello, hello. Hi.
Hi.
I'm Anna. Good job. I was just curious. You said in part, I might have missed something, but when you said like the subtrees, you extracted the relevant aspects of it. How do you like decide what's the relevant aspects for a specific subtree?
Yes, exactly. So this is also one of the main contributions of the paper itself, because the naive approach would be to basically just extract whether a property is satisfied or not. However, this approach is unsound, and there are quite a lot of counterexamples. So for each property we have, so this is the contribution of the paper. For example, we have to extract for which players the property is satisfied or not, for which cases it is satisfied, what are the practical utilities or not. So it really depends on the setting and the property that we are verifying.
Thank you.
Any other questions? So I have a quick question.
Yeah.
Maybe, so you decompose your problems into smaller bits that are much more easy to verify independently. But is there a case where you decompose too much the problem and it becomes too small, and at the end of the day you're doing maybe it's slower because the granularity is too small?
So I think it really depends on the benchmark. So generally, the new approach outperforms the old approach. However, there are some benchmarks where the structure of the benchmarks is way different than the others. So here it might be less efficient, but generally it performs better because the queries for the SMT solver become quite smaller and they're easier to handle for the solver.
Okay, thank you. Any other questions? All right, so.
Okay, hi, good morning everyone. So I'm Zheng Han, and I'll be presenting on our paper entitled Efficient Decrease and Conquer Linearizability Monitoring. So, what is linearizability? So linearizability is something that is introduced by Hurley and Wink in the 1990s, and ever since it has become the de facto correctness condition, the standard for deciding the correctness of concurrent objects. And the idea is that in a multi-threaded environment, the time window for which operations executes can overlap with some other operations from the other thread. And the idea of linearizability is that you can pick a specific time within this time window for each of these operations, whereby this operation, you say that this operation automatically executed in that time. And when you order the execution, and it still satisfies the specification of the object. So, for example, on the left, you can see a bad execution because clearly NQ2 came before NQ1 in the queue, but the Q1 came before the Q2. But on the right, it's a good execution because you can schedule NQ2 over here and the Q2 over here, then NQ1 over here and the Q1 over here. Yeah. But unfortunately, verifying whether implementations of arbitrary abstract data type, whether it's linearizable, this is undecidable. So we take a step back and take a pragmatic approach and ask a different question. So given an execution or history of a program, is it linearizable? So the answer has been answered in 1997 actually, that in general is NP-hard. And in fact, Gibbons showed that for the simplest data structures, such as read-write registers, that supports only read and write operations, even for that is NP-hard. And the next natural question to ask is whether there exists tractable variants of the problem. And actually, in the same paper, they also answer this as well. And there is a tractable variant of the problem. And they introduced this thing called the ambiguity restriction, which says that in this history, each value can only be returned once. And under this restriction, the history the problem becomes tractable. And then the next question to ask is whether the same can be applied to other data structures as well. And throughout the years, there have been multiple studies to try to generalize this to other data structures. In particular, in 2018, there's this study to categorize data structures into this thing called collection types, which includes stacks, queues, stacks, queues, and other commonly used data types. But unfortunately, there is a bug. A reduction is unsound, so that this problem becomes open again. So separately, there have been other studies that did not generalize, but study for individual data types under unambiguity restriction. Is this problem still tractable? And actually, Gibbons, not long after his first paper, actually he published another paper and says that for stack, queue, and priority queue, this problem is still tractable under the unambiguity restriction. And actually, earlier this year, unbeknownst to us, earlier this year in PLDI, there's another paper that is published, which improved on the complexity on stack to n square, and also give an algorithm for set that runs in linear time. So the problem with existing algorithms is, first, they do not handle peaks. Peaks are generally read-only operations on these data types. For example, for stack, you can see what's the element on top of the stack without actually popping it, and for queue as well. And another problem they don't handle is empty operations. So empty operations is intuitively operation that has failed. So in real-life programs, when you have concurrent objects, for example, you might want to try pop, and if that stack is empty, then the try pop will return as false, for example. So our paper introduced a few algorithms, and in particular, it improves the stack's time complexity to n log n, And as well as it can be generalized to handle peaks and field operations as well. So beyond that, our main contribution is to introduce this general framework, which is called decrease and conquer framework for this problem. And this idea is centered around this thing called linearizability preserving values, which I will introduce you in a moment. Yeah, so this is the algorithm for solving linearizability problem, given the unambiguity restriction. It's simple, it's 6 lines only, but I have not actually told you what this function actually does. So as the name suggests, this function gets the linearizability preserving value of the given history H. So you might ask, okay, what is linearizability preserving value? So a linearizability preserving value preserves linearizability. Yeah, so given a history, if you have a linearizability preserving value, you removed all the operations on that value, the remaining history is still linearizable. And vice versa, if the smaller history is linearizable, you add back the operations on that value, the entire history is also linearizable. So our job becomes easier, right? If given a history, we can just repetitively remove linearizability preserving values until it cannot be removed anymore. And if the remaining history is still non-empty, and then we can conclude that the history is not linearizable. Yeah, and we can actually improve the efficiency a little bit, and we can short circuit this and say that, okay, if halfway through we find out that the history must not be linearizable, then we can just return bottom as the linearizability preserving value. So yeah, the main result is that linearizability monitoring is polynomial time reducible to finding linearizability preserving values. And as a treat, I'll show you how you can find linearizability preserving value for stack. So for queues and priority queues, it's presented in the paper, and for more information, you can refer to it. But today, I can show you how you can find it for stack. So for stack, there's this thing called the potentially bottom value. So potentially bottom value is a value that is potentially at the bottom of the stack for some legal linearization for the history. And we have to show 2 things. One thing is that potentially bottom value is indeed a linearization preserving value. And second thing is that if there's no potentially bottom value, then the history is not linearizable. Then, as such, you can return bottom as the linearizability preserving value. So the first thing, but potentially bottom value is a linearizability preserving value. First, you can see that from the diagram, if you remove the operations for the value 1, the remaining blue instance is still going to be linearizable if the whole history is linearizable. And conversely, if the remaining history is linearizable, we can just squeeze the linearization into the gray part away from the red region. And then we can just put back the operations for push 1 and pop 1. And this is still going to be a legal linearization for the entire history. And the second point is that if a history is linearizable, then a potentially bottom value must exist. Why? Because you can just take any legal linearization and say, hey, the first value that is being pushed in is the potentially bottom value. So our approach for finding linearizability preserving value for stack can be naively implemented in ON square. And that means for the general linearizability monitoring problem, it can be done in N-cube. And actually, this can be further improved into n-log n if we use some other data structures to analyze the algorithm. And for example, segment trees, we use segment trees and interval trees to improve the time complexity to n-log n. Yeah, for more information, you can refer to the paper. Yeah, so we implemented our algorithms and run it in WSL Ubuntu and test it against existing tools. Our tool is shown that our tool is much faster for stack traces and for queue traces as well. And we also stress test our tool against history of up to 1 million operations, and it can be shown that it runs in less than a second. Yeah. So with that, I've come to the end of the presentation. Yeah.
Use the mic or the handheld?
Please wait. We have to start on time.
Okay.
Not early. So we have to wait for 4 minutes in order to start.
I got a present for you.
Hello，给你带了一个。哦，谢谢你。哦，我应该也给你带一点。哦，没事没事。OK。Yeah, long time no see.
Long time no see.
How it's going?
All good.
Oh, good.
So just came back to Singapore. It's not my first time here. I used to work in Singapore.
Oh, really?
Yeah.
It's my first time here.
But it's always good. I love Singapore. Singapore is a nice place.
Yeah, but I feel that the climate or everything is very similar with Hong Kong here.
To the summertime in Hong Kong. Yes, because Hong Kong is a winter. Here there's no winter.
Yeah. Very
Here is always the same.
Everything is so wet and hot. Yeah, and the air conditioner here is much cooler.
Yeah, I actually turned off the air conditioner in my hotel.
Yeah, it's too cold, right?
It's too cold. And I was fine.
Yeah.
Yeah, because of the corridor and all the other rooms.
Everything else
Yeah.
becomes maximum.
Yeah, I
So I
heard.
just turned it off because it was too cold, and I slept through the night, and I was fine.
Is it the Concorde?
No, it's just hotel.
Okay.
There's a
Same
few
thing in
stations
Concorde,
always.
yeah.
Yeah. They put it too cold. Yes.
And I tried to change it, and it just doesn't. It doesn't know how to blow less cold air. You know, even with the control. I don't know why.
Yeah.
It's very strange.
Yeah. I actually had during the day when I first turned it off, I actually had to open the windows to let the water air come.
It's like a fridge. So hotel rooms normally don't let you open the window. So that's you were lucky.
In my hotel they do.
I heard that Singaporean doing this because they want even people wear shoes don't feel hot inside indoor.
Right.
But
Yeah.
I heard, but I don't know whether it's
So
true.
so it's a
so
good reason
everyone-
for everyone to buy a jacket.
Yes.
We have a market for jackets.
Right. It's the big jacket who's pushing all this.
Jacket market, yeah.
Can you see everyone is wearing pants? All right. Okay, now it's on. Okay. All right. So for the next talk, Hansu will talk to us about merges. So please go ahead.
Okay. Yeah. Thank you. So today I'm going to talk about liberating merges via partners and guarded subtyping. I'm Han, and this is joint work with Xuejing and Bruno. So one word speaking, what we are trying to do is to develop a calculus that enjoys the merits of both OOP and FP language. We are doing so based on intersection types, and in prior work, we have studied the encoding of basic OOP data structures. So to begin with, let's first talk about intersection types and their calculus. Intersection type, namely, is the intersection of two types, can enjoy the feature of both types. Here is a program example where you use the program variable of intersection type. X is of the type int and bool, which is later passed to the evaluation context successor x and not x. Successor x requires x to be of type int, while not x requires x to be of type bool. Because x is of type int and bool, thus this program can pass type check successfully. So after we get the intersection type, the next natural question to ask is what terms are of intersection type? There are many ways to construct terms of intersection type, and here we follow the line of work of merge operator. Merge operator, denoted by double comma here, can merge arbitrary two terms together. Here, we merge one with true together to get a term of the type int and bool. And if we pass this one merge with true to the program variable above, then we'll get the following result. Successor function requires the parameter to be of type int, therefore, successor one merge with true will be finally evaluated to 2. Similarly, not one merge with true will be evaluated to false. What we are interested in this merge operator is that it offers very good compositionality. Whenever we want to compose two objects, even different objects like integers and Boolean, all we need to do is to merge them together with a merge operator. However, merge operator comes at its limitation. That is, it has a non-deterministic semantics. So in 2016, Oliveira proposed the disjoint intersection type to pose disjoint restriction on merge operator to make this calculus deterministic. Disjointness is a relation on two types, suggesting that two types has nothing in common, or we say the common supertype of two types can only be top. And let's see two examples. Here, the first example is one merge with true. One has a type int, while true has a type bool. Since int and bool has nothing in common, therefore, these two types are disjoint, and we can merge them safely. However, we are not able to merge one with two because both of the terms have the type int. Their common supertype can be int, which is a non-top type, and this merge has a non-deterministic semantics, where one merge with two can be evaluated to either 1 or 2. These are the basics of the disjoint intersection type and the merge operator. And next is our work. So the problem we found with disjoint intersection type is that it is too restrictive in that some of the useful feature like function overloading is not doable inside the intersection type calculus. Function overloading is one kind of feature that is shared in many programming languages. It is one kind of polymorphism over parameter. It allows you to implement many versions of function for one function. Such as on the left-hand side, you got a function overloading example in C++, where you got two add functions. One add is for add int, the other add is add double. So in the subsequent program, whenever you want to add two things, you only need to write the function name add and let compiler decide which version or implementation is the correct one to use in the context. And Haskell shares a similar feature of function overloading. And here we demonstrate the example function show. Show is a function will convert everything into a string. And here the type class defines the interface for the showInt and showBool, which converts integers and Boolean into string. What interested us is that this idea of function overloading is very similar to what we have in merge operator. The idea of enjoying many different implementations for one function simultaneously is the idea of we are doing with merge operator. So if we are going to implement the function overloading example in our intersection type calculus, all we need to do is to merge different implementations together, such as on the left-hand side, the C++ example. If we want to implement this, all we need to do is merge the two different implementations of add together. However, we cannot do the example on the right-hand side, and let's see why. Suppose we got a showInt, which converts integer to string, and a showBool, which converts a Boolean to string. If we are trying to merge these two functions together, it gets rejected in the disjoint intersection type because it finds a common supertype of int and bool to string, which is a conflict identified by disjoint intersection type, and we are going to change it. So the next step is to change the conflict resolution inside the intersection type calculus. What we do is to look into the current OOP language design, and we find a feature called delayed conflict resolution, which will be introduced at the next slide. So what we do is to take inspiration from such mechanism, and we also like to provide some insight towards it. And let's talk about conflict resolution. So in disjoint intersection type, the conflicts are identified as non-top common supertype. And in OOPs, conflicts are usually conflicts between data structures and names, such as we got two records here. The first record is x1, y false, and the second record is y true, z true. If you are going to merge these two records together, we identify a conflict in the label y, because both of the records has a label y. And then we have to do the conflict resolution for them. There are basically two categories of conflict resolution, the immediate one or the delayed one. The immediate one requires you to resolve it once you discover it, such as you either resolve it by hand by removing one of the y labels inside one of the records, or you let compiler automatically do the job for you. Most of the programming language and our previous intersection type calculus do an immediate resolution. However, a delayed resolution is also possible, where we don't abort the program once we find the ambiguity. We later abort the program when we use it. And here is a delayed conflict resolution example inside C++. Here, suppose we got two classes. One is the class stack, and the other is the class drawable. Both of the class has a virtual function method called draw. You may find that the draw function have different implementation inside the two classes. However, when we define a third class called the drawable deck, which inherits these two classes, the C++ accepts it. It will later abort the program when you call the draw method of drawable deck, but at this stage, the drawable deck is accepted. So the delayed conflict resolution is to delay the conflict resolution, conflicts until you use it. So we take inspiration of it, and what we are trying to do is to delay the conflicts between the function overloading until we use it. And we are going to show this by the example of showInt merged with showBool. Okay, so this is a diagram of the showInt and showBool in terms of the subtyping relation, where showInt has a type of int to string, while showBool has a type of bool to string. The middle gray part is the overlapped part, which is a common supertype of both types. So what disjoint intersection type do is it adopts a very conservative way of dealing with conflict. That is, whenever we find any overlapping between two types, we reject the merge of them. However, in the view of delayed conflict resolution, we can delay such conflicts. We are happy with two terms merged together as long as we have methodologies to tell them apart. So here, in this simple case, in the non-intersection type case, for types like int and bool, we say they are not conflicting as long as they are not subtype of each other. So this is the new conflict notions for our paper, and this is all we need to do is to generalize these conflicts to the general types like intersection types. For intersection types, they can view as a series of non-intersection types merged together, and we illustrate using the concept of type components. So our apartness, our conflict notion is that we say A is not conflicting with B as long as all of their subparts, subcomponents, or we say the non-intersection types are not subtype of each other. So this is the first notion of our paper, which is apartness, and there are more things to do. So for disjoint intersection types, the disjointness defines the notion of conflicts, and the subtyping is for the safety checking. In our work, we have relaxed the disjointness to apartness. Therefore, we need to strengthen the subtyping to the guarded subtyping. And let's illustrate the guarded subtyping. So here is a type of int to string and bool to string, and the sum of its supertype. And this diagram, each green arrow denotes a relation of supertype, And you can see the int2string and bool2string has a supertype of int2string and also has a supertype of int and bool2string. What happens in the disjoint intersection type is that we allow no ambiguity or no overlapping inside any of the type. So whenever we want to cast a type or coerce a type to another type, as long as there is a subtype relation, we are happy with it. However, inside the apart intersection type, it is not the case. The type int and int2string and bool2string may come from some overlapping merges like showInt merged with showbool. If we are going to coerce the showInt merged with showbool to the bottom type int and bool2string, then we don't know whether the final terms come from the part int2string or it comes from the part bool2string. Therefore, we strengthen the subtyping to a notion of guarded subtyping. That is, it is a guarded subtyping of B when there exists unique coercion from type A to type B. We replace all of the subtype checking by the guarded subtyping checking inside the type system to gain the determinism of our apart intersection type calculus. So these are the two notions of our paper, and there are some of the other things we provide in our work. The first serial-theoretical consequence of the of our apart intersection type is that we are able to have complete conflict resolution. Inside disjoint intersection type, we pose a disjoint restriction so that any types can be merged only when their common supertype is top. This results in some of the conflicts cannot be resolved. However, in our relaxed apartness, all of the conflicts can be resolved, and even better, it can be resolved automatically. Besides, we talk about apartness and guarded subtyping in terms of the language of specification, but to put them into practical usage, we have to develop algorithm for them. We also include that in our paper. Furthermore, we provide source and target calculus, which encode all of our examples, and we show that the soundness of embedding such mechanism into an intersection type calculus. Finally, all of our theorems and lemmas are formalized in ROC. And thank you for your attention.
Thank you for the talk. Can you go back one slide, please? Yeah. This looks to me like you do covariant function subtyping, because int to string, is that really a subtype of int and bool to string? That seems wrong comparing with the arrow rule, or I misunderstand something.
Sorry, just the voice is a bit low.
Okay.
Okay.
So if we look at the arrow int to string, is that a subtype of int and bool to string?
Yeah.
But that violates the contravariance rules for functions, so I'm confused.
The error is a supertype relation.
The
error is the supertype relation. The reverse is the subtype relation.
Yeah. Okay.
So
sorry, I got it the wrong way. Yeah. Sorry. Thanks for clearing that up. Thank you.
Any other questions? Yep.
Hi. I noticed with your merge operator, it seems like, or at least with the disjointness version, so maybe the partness corrects this, and I'm curious to understand. It seems like if you have more precise information about your expressions, you're more likely to reject the expression.
Yes.
Wouldn't you want more precise information to make it more likely the program is acceptable?
There are two parts of it. If you merge too many things, then it has a stronger possibility to have conflicts between these things. But if you make things more precise, in our case, it is to make a type to be a subtype. In this case, it will have less conflicts. I don't know how to illustrate this. So, such as the example here, you got int to string and bool to string, and if you merge more and more things in the top type, in the topmost type, then it has more possibilities to have conflicts. But if you are going to make things more precise, it is actually going way down here. And if you make one part of the things more precise, it has less possibility of conflicts because you know more about the things, so it has less chance to conflict with the things that is very coarse.
Cool. Thank you.
Thank you.
I had a little question. So do you have unions in your system?
Sorry.
Yes. No, but it's fine. Do you have union types in your system?
No. Actually, we had one version of union type, but it has some conflicts with the distributivity rules in the subtyping for intersection type. And we tried a lot, but we don't know how to fix it. So finally, in our presentation, we only got the intersection type. But it's a worse direction to explore in our future work.
Okay, cool. Thanks. Yeah. Okay, thanks the speaker again. Right. Is it working?
I'll switch. There's another one. Okay, I'll just change the other one.
Maybe try.
Yeah.
Try this one. All right. Now Matthew will tell us about the simple essence of monomorphization. Please go ahead.
Thank you. We compiler developers have a bit of a problem, and that's that the low-level languages like x86 assembly, the makers of those refuse to add polymorphism to their language. And the same can be said for Java bytecode and ARM and LLVM. None of these support parametric polymorphism. And so when we write code that looks like this, where we have some function with a type parameter A, we need to do a bit of extra work to get this to compile down to that low-level code. There are a couple options for doing this. We can do the Java route, which is erasure. We can go the Rust route and do monomorphization, and maybe there are some other things. But if you remember the title slide of this talk, you'll know that I'm talking today about monomorphization. The basic idea of monomorphization is that we're going to be making a copy of each function for each type it's instantiated with. So if, again, we look at that function that I showed before, this ID function, it has a type parameter A, and we call it here twice, once with int and once with string. To monomorphize it, we're going to duplicate the function ID. We're going to have one specialized version ID int, one specialized version ID string, and then in each of those places, we're going to call the respective function, ID int or ID string. Monomorphization is a transitive transformation. So here we have added a function called twice. It calls ID twice, and it itself is called twice. We call it once with int and once with string. And when we do the translation, we need to duplicate both of these functions. We need to duplicate ID, and we need to duplicate twice. And we end up with a total of 4 functions. And of course, we need to change all of the calls to those functions as well. So you're all experts now on monomorphization. What do we do about this? And in particular, what do we do about that parameter f, which itself is a polymorphic function? That syntax there means for all z, z to z. Maybe you have kind of an idea of how you might do it, but it gets trickier. And you could be forgiven for thinking that this isn't even possible. It has been said that high-rank types cannot be monomorphized at all. It has been said that monomorphization cannot be done for higher-rank first-class polymorphic functions. It has been said that some polymorphism cannot be specialized statically, polymorphic recursion, first-class polymorphism. And this is what I would classify as glass half-empty talk. We are going to take a different perspective. We're going to say it is possible with some restrictions, and we're going to clarify exactly what those restrictions are. So today I'm going to be presenting a simple monomorphization method that supports higher rank and existential types. The key ideas here are that we are going to monomorphize a high-level language, and we're going to monomorphize via what we call a type flow. Now, when I say a high-level language, I mean our language is going to look like this. We'll have a source language which has polymorphic functions like we've seen, but then we'll have polymorphic enums like the option type, polymorphic traits like the show type, and then the target language is also high-level. It's all those same things, but in the monomorphic respective version. The type flow directed monomorphization has 3 steps: constraint collection, constraint solving, and specialization. The idea of constraint collection is that we're going to find which types flow directly into which type variables. So again, if we look at this original example, we can look at how the concrete types, int and string, will flow among the a and b variables. When we look at how twice is called twice, we see that int and string flow into b, and in the body of twice, b flows into a. And so we get a set of constraints that look like this: int into b, string into b, b into a. The next step is constraint solving, where we'll find which types flow transitively into which type variables. So we'll take those constraints that we had, and we can turn it into a nice looking graph. And then we can clearly see eventually everything, both int and string, will flow into b and into a. And so we get a solution that looks like this. A maps to int and string, and b maps to int and string. And with this solution, we can take our original program, and we're going to replicate each declaration for each type in the solution. So we need to replicate ID for int and string, and we need to replicate twice, once for int and once for string. So this is nice, but it's also boring because this is what I showed at the beginning, and I promised higher rank functions. So let's take another look at that initial program. So the first step to handling this is that we need to translate it into our language. And the way we're going to do this is something like how Java represents functions. We're going to take that higher rank function f, and we're going to turn it into a trait. So we introduce this trait, we call it ID, and ID has an apply method, which has the same signature as that higher rank function. Then down below, we have ID itself, an instantiation of that trait. And then in the body of the app pair function, we apply that method of the ID trait to x and to y. From here, it's exactly the same as what we had before. So we're going to get some constraints out of the program. Specifically, from the app pair function, we can clearly see that int flows into x and bool flows into y. From the trait ID, we have a flow from the apply method in the trait to the apply method in all of the instantiations of the trait. And then in the body of the app pair function, we can see that x flows into z and y flows into z. And again, we do the same thing as before. We'll take these constraints, make a nice graph for the audience, and we will see how everything flows. Int and bool will both flow into z and into a. Int flows into x, bool flows into y, and we have our solution. The next step is to apply it to the program, and just as before, we'll duplicate some things. Here, a trait ID now has 2 methods in it, one for apply int, one for apply bool. The instantiation of ID also has those 2 methods, and then the app pair function will call the respective method of the ID trait. Now, this can handle all forms of polymorphism, and it's always handled in the same way. So polymorphic functions, polymorphic types, existential types, and higher rank types all can be handled in the same way. Now, you'll recall I had an asterisk on the first, or one of the first slides, and that's because we can't do it all the time. And when we can't do it is when we have polymorphic recursion. So here I have a program which exhibits polymorphic recursion. I have this function foo, and it calls itself. And clearly, first of all, it won't terminate. But as well, when we try to generate code for that we can't do that either, because foo calls itself with a larger type. So if we try to generate constraints from this, well, we can generate the constraints. But one of them is this box A into A constraint. And when we show this on the graph, we have a labeled edge with box. And what this means when we evaluate these constraints is that we're going to trace where int flows among these. So the first step, int, clearly flows into A. But then when we go along that box edge, we need to apply that constructor to int. And so we go along that edge, and we get box of int. That's fine. But then we need to keep going along that edge, right? And we get box of int, and box of int. And it's clear that we have an infinite solution here. And there's no way to monomorphize that. And so we can generalize this kind of idea as a growing cycle. Any cycle which features a type constructor like that is going to be problematic for our monomorphization system. The nice news is that all forms of polymorphic recursion are uniformly detectable in this way. So they all show up as growing cycles. This includes polymorphic recursive functions, methods, and types, as well as what we call polymorphic packing, which is the case for polymorphic recursion in existential types. We have some meta theory. I won't talk about it, only to say that we have shown that our monomorphization system preserves semantics as we translate from the original to the monomorphized language. And we also have an implementation. Here you can see we have the input, we have a desugaring, and then down below there are some constraints, and the solution, and finally the monomorphized program. So in summary, I've shown a type flow-based monomorphization supporting higher rank types. We have 4 types of polymorphic recursion. We have a calculus and type system, which supports semantics preservation, as well as an implementation. If you want to learn more, there's the paper at that link. That's all. Thank you.
Hi, this is very nice. So you have this constraint solving algorithm. You generate the constraints. It either succeeds or fails. Do you have some other kind of crisp characterization of when it's always going to succeed? Or is it just throw it at the constraint solver and see what it says?
I mean, the constraint solver is very simple. So it's not like an SMT solver or something where it's very crazy. It's a fixed point computation, and if it has a cycle in this graph, then it's going a growing cycle in the graph, then it fails.
And I'm kind of getting at is, as a programmer, are there some more structured ways that I know that my program's going to work, or?
It's a non-local property, and so
no,
it's very
maybe.
difficult to determine.
Okay. Yeah. Thanks.
Hi, very nice work. So in 2019, we published a paper on language called SPLASH'25, which is a system F. And then we have a follow-up paper which says how to compile it in LLVM, for which we built a type flow analysis, which seems very similar to you. That was 5 years ago. Did you compare to that? And if you did, what are the differences?
I'm afraid I'm not familiar with that.
Okay.
Have lunch together. So one way to deal with the polymorphic recursion question might be, instead of making a fresh copy for every data type, just make I'm sure you thought of this, just make a fresh copy for each different representation. Because after all, Intel, you only need one copy for functions that manipulate pointers, right? Yeah. Another copy for single precision floats, and so there's only a finite number of copies you ever need, and then you can close the recursion. Suddenly you can say, no exceptions, I can monomorphize everything. Wouldn't that be great? I mean, you must have thought of that and tried it.
Yeah, I mean, it would be great. I think this is a simple essence, and so that we consider that kind of thing just a little bit of an extension that is a little bit outside of what we call the essence. But yeah.
Okay, but this is a simple but wasteful essence.
Yeah,
right?
Perhaps, yes.
So make it. So the other question I had was to do with this is a kind of whole program analysis.
Yes.
Isn't it? So even if you've got a data type that contains a function, polymorphic function, well then every client of that data type out there in the world, you can't do any separate compilation at all with this system. Is that right? I mean, that is a problem in practice, isn't it?
That's correct. There's no form of separate compilation.
Okay, so does that mean, game over? Because the real world is full of separate compilation, isn't it? So
there are a lot of programming languages that don't have separate compilation. I mean, I suspect.
Mainstream use.
I want to say Rust. Yeah, okay.
Rust is a whole program compiler? okay? Cool. Whole program, yes. I know, Milton, yeah, that's right. And you get lots of juice from that.
Okay, we don't have time for other questions, sorry. So let's thank the speaker again.
Sorry?
You prefer this?
I prefer this. I will like have a presenter's view here. Play in window. Oops.
All right, so Ichen, please tell us what's in the box.
1 second. I need to find out where is the presentation. Oh, okay. Oh, this shouldn't be. Okay, it's for me. Okay, so hi everyone, and welcome to my talk. I'll be presenting what's in the box, which is extending capture checking to handle generic data types properly. And I'm Yicheng, and this work is co-authored with Oliver, Nguyen, and my advisor Martin. So generic data types, they are everywhere, of course. They are in real programming, they are everywhere, and they are a fundamental thing. But for capture checking, which is a recently proposed effect and resource tracking system for Scala, it actually remains unclear how it can interact with them. And this work actually fills this gap. And we propose system calculus, which is a new foundation calculus that handles generic data types properly. And it's minimal, it's expressive, and we think it would be a perfect foundation for capture checking and its follow-up extensions. And more importantly, with it, we have a principled understanding of how to track captures over generic data types. And then with the latest calculus informed capture checking implementation, we successfully capture checked the entire Scala collections library. And we think this is, of course, a key prerequisite for capture checking to be practical. And so maybe first thing first, what is capture checking? And shortly, this is a type system for tracking effects and resources in Scala. And we have quite an ambitious goal. We want to bring effect tracking to all Scala users and not just a research prototype. And this would require, in particular, lightweight notation, minimal disruption to existing code, because Scala is like a highly established ecosystem. And the essence of capture checking is quite simple. So first we have capabilities, and all effects accessed via capabilities. And we represent capabilities as just program variables in our programs. And the second is capturing types. So we argument types to track what capabilities or variables the value will capture. And that's the type we'll talk about the effects of this value. So first, let's talk about capabilities, and it is quite a established idea. For instance, Wyvern is famous for using capabilities, and programs will use capabilities to perform effects and access resources. And for instance, here we have a console capability for accessing console I/O and a file capability that provides access to a file in the file system, and a cancel div by zero capability representing the permission to throw a exception, which is a control effect. And these capabilities are represented as the program variables. So for instance, in this program, we assume we have a console capability at hand, and here the caret marks the capability to be tracked by our system, and we can write a greet function that prints a greeting to someone to the console. Okay. Yes. And now we talk about capturing types, and here is the syntax, and there are two parts. So the shape type tells you what the value is. It's an integer or a function, whatever. And the capture sets will tell you what variables or capabilities it might capture and use. And so back to our greeting function, this type will be string to unit capturing console, and the capture set makes the effect explicit that this function may perform some console I/O. And there have been decades of research on the effect system. So why capture checking? Is it like just yet another effect system? So let's recall our ambitious goal that we want to bring capture checking to the mass. And Scala has a quite established ecosystem and a lot of existing code. And this means that we will not be able to start fresh. And we need an effect system that can be retrofitted into established code bases with minimal disruption. And that's what capture checking is for. And to achieve this, there are actually two key ingredients. One is the lightweight capture polymorphism, and the second is boxes. So first, for lightweight capture polymorphism, let's look at the classical map example, list map example in CC. And surprisingly, its signature stays identical to the previous one. And how would that work? Under the hood, so in CC, we have the universal capability cap. And here, the T fat RLU is actually an alias for T2U capturing cap. And the cap is like the top capability in the system that governs everything in the world. So effectively, every capture set is a subcapture of cap. And here, subcapturing will be like subtyping, but for capture sets and capabilities. So this is analogous how objects work for subtype polymorphism. And here, map is taking a function that could perform any effects. So it's effectively polymorphic over the effects of F. So now let's look at the non-eager version of this mapping operation, the map of iterators. And this capture notation is the only change from the vanilla version. So this signature says that the resulting iterator can perform the effect of the input iterator and also the effect of the function f. So here, the name of f also becomes the effect it will perform. Yeah. So now boxes. So when a capability is put into a box, it will become pure. Like here, when we have a file capability, if we box it, it will become pure. And then to use what is boxed, we must do an unbox. And when we unbox, the box capture set will like be popped out and charged to the environment. Like here, if we write a function that opens the previous box and use the file capability, it will capture F. And this entire process is called capture tunneling. And now we have the key design choice that generic types have always be boxed or pure. And I don't go to the details of this design choice, that they are a key mechanism to ensure the lifetime of capabilities and essential to writing generic operations in a clean and expressive way. So all these ideas have been formalized in CC Subbox, published in Top Plus. So far so good, then why do we need another new foundation for capture checking? And the problem is when we are actually making everything practical and try to capture checking more and more things, we found that there are more problems. So it's again with generic data types. So CC Subbox has one restriction that you cannot unbox a cap. And do you see this box impure function? It type says it captures cap, the universal capability. And CC will disallow unboxing this boxed computation. And this rule exists mainly for scope safety, and we don't have time to dive into it too. But the intuition is quite simple, that the cap means everything, and it's just too permissive to allowing unboxing anything. And so to do this restriction, this perfectly reasonable code will not work in the previous system. So here, this make iterator function takes a list of computation, and each is computing an integer. And we want to make this list of computation into an iterator for integer. And I want to know that the parts in gray will not be in the surface language. They are always inferred by the compiler, like all the box types. And we will have the error here that when we try to unbox the computation in the list, its type is actually capturing cap under the box. So effectively, we cannot access what's in the box. So let's have a post-mortem of this failing example. So the intention of this cap in the parameter is actually to convey that this make iterator function should be polymorphic over the effect under the boxes in the list. But because the cap occurs inside the box, this effectively prevents us from accessing anything inside the list elements. So it seems that the CC's lightweight polymorphism is falling short. And in fact, with explicit polymorphism, we can express this function in a natural and a principled way. Like here, we can universally quantify a capture set, and then the resulting iterator will be capturing this universal capture set C, which is precisely what it is. And explicit polymorphism is providing us with a clean solution to this problem, but this is what the previous CC doesn't have, actually. So, and that's why now we have system couplers, and this is a new formalization of the capture checking approach, but it drops the universal capability cap, and instead it's introducing explicit quantification, both universal and existential. And but this is actually going the opposite way of the existing CC system. So recall our ambitious goal that to integrate the effect and resource checking into Scala. So our system must actually be quite non-intrusive and flexible, and that's why CC was advocating for its lightweight polymorphism to avoid the overhead of explicit polymorphism. But now are we going exactly the opposite? But the short answer is not quite. So for the majority of the code, like the list mapping functions we see here, we still want to write it in the implicit style. And we don't want to write code this way, which requires adding effect parameters to every single higher order functions in the library. But on the other hand, when CC's lightweight notations for short, we still want to express these functions, like this make iterator example. So this is essentially a design trade-off. Like on the one hand, we have the lightweight style, which is minimal notation overhead, but the expressive is limited. And we have the implicit style, which has some intrusive notation overhead, but the expressiveness will be optimal. So what shall we do then? So, but why do we have to choose? So we don't have to choose. We can offer both in the system. Then it's up to the user to decide which style to use. So we can use lightweight style when it fits, and when it falls short, we can use the explicit style to regain the full expressiveness. And moreover, now that we have the system couplers, which is like the formalism of these explicit quantification, which have a principled foundation for capture checking, we can also understand all these lightweight notations by a translation to them. And then that's why we also have system real cap, and it formalizes all the lightweight notations we have in capture checking, and they are understood via a type-preserving translation or compilation to couplers. And moreover, we also offer like lightweight notations for capture polymorphism under boxes. So instead of writing the function this way, which is what we think, you can equivalently write it this way, and but that doesn't require any explicit capture parameters. And the ops star here is the rich capability of the parameter ops, and intuitively it represents what's in the box of ops. And this new formalism is informing a redesign of the capture checker, and there's no need to read this table. I will explain it to you. So with it, we successfully capture checkers the Scala collections library, and the collections library is of course really highly generic. But the vast majority of classes do not even need signature changes, like list mapping. We have talked about it, and for the parts that needs signature changes, we need to add more capture notations. But no explicit quantification is needed. The lightweight notation with the rich capabilities we just saw on the last slide is sufficient for capture checking the entire standard library. And the capture check library is already in nightly version of Scala 3, and it will be officially shipped in Scala 3.8. And the credits should go especially to my colleagues Wuyen and Hamza, who did most of the work for this capture check library to be shipped. And this is a short talk, so we cannot cover everything, but there's some more things. So the meta theory is completely mechanized in Lin4. And furthermore, we have the couplers, which is now a great foundation system for starting various extensions. So there's a lot of extensions that's under development. So for instance, system capybara, it brings like separation and freshness reasoning to Scala. That's the goal. And I had a talk on Tuesday already. And more things like class capabilities and the interaction between capture checking and the classes, etc. And you can check our paper for more details, and also the website. And thank you for listening.
All right, any questions?
This is on. Thank you for the talk. So I have two questions. I guess the first one is, so I was interested in the fact that, so you added reach capabilities, the explanation for them was great, but I was curious, is there a reason why they needed a separate notation? Is there ever a time when the user writes an annotation, they include a box, and they don't mean the capabilities under the box? Is there a need for the star? For example, if you go back to your example, could you have just written ops? Of course, this means something different, but maybe the user never means I capture the box and not the capabilities inside the box.
Yeah, like the example here.
Yeah.
Sorry, I didn't get the question. Could you?
So the question is, do I ever write an annotation where I capture a box, and I don't mean I also want all the stuff inside the box? Like, do you need a notation that is the star? Because I have just written ops here. Because maybe I just mean I always want the thing inside the box.
So we need a star here because ops in theory just means like the top level capture set of ops, which
right,
is
but
empty
I mean,
here.
if I'm capturing ops, do I ever just want the top level capture set of ops? If it's a box?
So for instance, consider the operation that concatenates two iterators. So it gives you a new iterator, it does not go inside the box, it doesn't execute the iterator,
Okay.
it just gives you the concatenation.
Okay, yeah.
So that's an example.
Okay, thank you.
Okay.
With an observation that might actually either convince me I understand this or convince me that I've no absolutely clue. Presumably the unpacking, or what you're allowed to do once you've unpacked, is different. So if you only have a capability for the box, all you can do is get this thing out of the box, and it's not saying you can do anything with, to use the title of the paper, what's in the box. But if you've got the star capability, it's saying not only can I unpack the box, I can do with that's in the box.
Yeah, it's
basically you unpack to do something. So for us, it's the same thing. So basically, you can't unpack the box without representing the capability that's hidden in the box.
So then that goes back to Isaac's question.
Well, a
Okay.
concatenation iterator
Maybe
can just concatenate the boxes. It doesn't need to go inside the boxes, right? The boxes are the operations that
all right, so let's keep this discussion and thank the speaker again. This is the end of the session.
we have to use that?
No, this is for me.
Okay, good.
Should I test it or anything?
It should work. I'll
Testing, testing.
I'll keep it muted for the most part. Whenever
Okay.
you need to speak, I'll unmute it, just so there's no like static.
Sounds great.
And then every other speaker will use a put-on mic.
Okay.
Yeah. Let me know if you give a shit.
Will do. Thank you.
Sorry. That was a nice coincidence. I saw it on the podium and I was like, I know this pen of Orchid. I've seen it. Yeah, nice. So
I was excited to see that when like I got like a Google Scholar thing. It's like, oh, we're building on this thing. Oh, nice.
Yeah, it's quite excited. I basically
All right. So welcome everyone to the reasoning session. Oh, bad feedback. Okay. Glad to kick things off with Elaine telling us about protocols.
Hi everyone, my name is Elaine. I'm a faculty fellow at NYU, and this is joint work with Felix Stutz, my PhD advisor, Thomas Wies, and Damien Zufray. In this paper, we study the implementability problem for global protocols with infinite states and data. Here is an example. In this two-bidder protocol, we have 3 participants, 2 book bidders and a book seller. The protocol commences with the first bidder sending the ISBN number of a book that it wishes to purchase to the seller and the other bidder. The seller responds with a positive integer denoting the price of the book, after which the 2 bidders enter a bidding loop. The loop tracks 2 variables that store the respective last bids made by each bidder, and notice here that the refinements enforce that bids are made in strictly increasing order. So the first bidder proposes a bid, the second bidder responds, and if the sum of the 2 bids doesn't yet exceed the price of the book, then the bidding will continue. At any point in time, the second bidder can indicate its desire to exit the bidding loop by sending a quit message to the seller, which the seller then forwards to the first bidder. Or if at some point in time the bidding is successful, the first bidder, who knows the price of the book, will send a success message to the seller, which the seller will forward to the second bidder, thus terminating the protocol successfully. Writing an implementation for each of these participants individually in a way that is free from communication errors such as orphan messages and unspecified receptions, and also free from deadlocks, is challenging. As a result, the construct of a global protocol has been proposed by multiple verification communities. A global protocol specifies the behavior of all participants' message passing actions from a bird's eye view and synchronously, thus ruling out large classes of communication errors by construction. These global protocols have been studied as early as the 90s in the form of high-level message sequence charts, and are also prominently featured in more contemporary programming language frameworks, including session types and choreographic programming. The natural next step in such a global protocol-centric methodology is to automatically synthesize correct by construction distributed implementations, one for each of the participants in the protocol. As with any synthesis question, one must first address the realizability question, which in our setting we call implementability, which asks, given a global protocol, does there exist a distributed implementation that can inherit all of the desirable properties? We take a formal language theoretic view on protocols and their implementations, which means that for us, implementability amounts to a language equality question. So on one side of the equality, we have the protocol semantics for the global protocol. These can be thought of as generalized symbolic register automata, lifting constraints on the way that registers can be updated as well as on the background theory. So the global protocol features symbolic transitions that are concretized to a potentially infinite set of concrete transitions with register and communication variables instantiated to values from the data domain. These concrete transitions form runs that jointly specify a total ordering of events per participant, as well as a coordination among events from different participants. So for example, the exchange of the success message cannot occur on a run that also exchanges the quit message. From these concrete runs, we obtain synchronous traces, and we split each synchronous alphabet into its send and receive counterpart to obtain canonically ordered asynchronous traces. We then close these asynchronous traces under a notion of equivalence that's specific to our target implementation model, which are communicating labeled transition systems. These generalize Brandon Zafiropoulos' communicating state machines to potentially infinite state devices for each participant that are connected through some network. In our setting, we study peer-to-peer FIFO channels. So this is a network that supports message delay and reordering, but not dropping or duplication. So with this, we can define the implementability question as, given a global protocol, does there exist an implementation in the form of a CLTS such that the language of the global protocol is equal to the language recognized by the CLTS, and moreover, we require the CLTS to be deadlock-free. As an example of non-implementability, consider if we add the following conjunct to our two-bidder example that requires that the second bidder never place bids that exceed the price of the book, meaning that the two bidders must make non-zero contributions each. This protocol now becomes non-implementable because these two bidders don't have equal access to information. In particular, the second bidder does not know the price of the book and therefore cannot always send bids that satisfy this constraint. In general, when our protocols allow global variables, non-implementability is very easy to run into. And here is a minimal example that doesn't contain branching or recursion, just 3 participants and 3 message exchanges. So participant P first sends to Q an integer x. Q then sends to R an integer y that is greater than x, after which R sends to P an integer z that is greater than x. So because R does not know the value of x, it only knows that x is an integer smaller than y, it cannot exhibit all values of z that satisfy this constraint. Prior work has attempted to address this issue by introducing a notion of known and unknown variables. So a variable is known to a participant if it is either the sender or receiver, and unknown otherwise. Based on this classification, x is known to P and Q, y is known to Q and R, z is known to R and P. However, in this predicate here involving R, x is mentioned, which is not known to R, and therefore this protocol would be rejected as non-implementable. However, this syntactic classification is only a sound approximation, and here is another protocol that admits the exact same syntactic classification of known and unknown variables, yet is implementable. And the only change that I've made here is to change the predicate y greater than x to y equal to x, so that R can indirectly infer the exact value of x through the value of y. In our work, we take a different approach. Instead of analyzing the symbolic protocol directly, we instead look to its concretization to explain sources of non-implementability. And it turns out that for this protocol, non-implementability boils down to the existence of these 2 concrete runs in the protocol. In these 2 runs, the values of x are instantiated with 2 and 3 respectively. Y is instantiated to 4 for both of them. And now z is instantiated to 3. In the top run, R sending to P the value 3 continues to satisfy the protocol, whereas in the bottom run, R sending to P3 constitutes a protocol violation, because 3 is not greater than the value of x, which is 3. However, from the pre-states of both of these transitions for R, these 2 runs are indistinguishable to participant R. Yet, performing one action on one run constitutes a violation, whereas the other is agreeable. We formalize this intuition into a set of coherence conditions that are 2 hyperproperties. In a nutshell, they say that from 2 locally indistinguishable global states, a participant can either send a message that's permissible from both states and thus continue to not distinguish the states, or it can receive a message that uniquely tells it which of the 2 states it's on, but in the presence of uncertainty, it cannot choose between sending or receiving a message. We show that this characterization is a precise characterization of implementability for concrete infinite state protocols. So the first step in our decision procedure for implementability is this reachability and co-reachability reduction from implementability to these coherence conditions. The coherence conditions are defined in terms of variance of reachability, and from it we immediately derive a finite algorithm for deciding implementability on explicit finite state protocols. In the second step, we define these notions of reachability as least and greatest fixed points over some background theory. This constitutes a mu-CLP reduction. Mu-CLP is a fixed point logic, first order fixed point logic modulo some background theory. And we use this to obtain a symbolic algorithm that is defined in terms of mu-CLP predicates. This constitutes a symbolic algorithm for deciding implementability that is defined on symbolic protocols directly. We use our characterization to derive the following complexity results. For the fragment of symbolic protocols over Boolean variables, implementability is p-space complete. For explicit non-symbolic finite protocols, implementability is co-NP complete. And for the fragment of syntactically defined multi-party session types, implementability remains co-NP complete. The hardness is via reduction from 3-sat, and in particular, the condition that dominates the hardness is the second one, that determines whether a particular message is receivable from a particular control state within a global protocol. Finally, I'll mention implications on synthesis. So our results show that synthesis is as hard as determinizing the automata fragment corresponding to the protocol specification, meaning that for all finite fragments, subset construction is a sound and complete synthesis algorithm. And for various non-finite fragments with determinization procedures, they can be used off the shelf directly to synthesize implementations. In conclusion, our paper presents the first sound and relatively complete algorithm for deciding implementability of symbolic global protocols. It improves on prior work along the dimensions of expressivity, completeness, and complexity. And we also implemented our mu-CLP reduction in a CAV paper earlier this year, as well as we mechanized our preciseness theorem in the rock prover. Thank you for your attention, and I'll be happy to take any questions.
Okay, questions, please line up at the mic.
This is very cool work, thank you. I was wondering to what extent your results are modular with respect to the network protocol that you chose. If I want to choose something other than pairs of FIFO queues, can I reuse some of your mechanism, or do I have to reprove a lot of things?
There is a current paper under submission that addresses this question, particularly along the dimensions of network models. So we study abstract network models that include things like global message soup and mailbox, FIFO queues, and so on. And the results partially generalize under certain assumptions on the abstract network.
I look forward to that getting in.
I have a question. Can you imagine a generalization of this framework to handle cryptographic protocols, where one way a protocol might be unimplementable is if it assumes parties can magically break encryption or something like that?
That would require some encoding. So our view on the problem is very extensional, meaning that we can only model message passing behaviors, sending and receiving of a message. So if you could encode violations as message passing, then that would be possible. But we can't guarantee things like local state properties, for example, not directly.
Got it. Thanks. Any other questions? We have 2 minutes left, I believe. Looks like not, so thank you again. Now we have plenty of time for the next speaker to plug in, and we could either hand the next speaker this handheld microphone, or they could use the clip-on, up to their choice. Yeah, okay. Okay, so I think we're ready to go with Lauren telling us about checking properties of database systems.
I don't think so. Maybe I can just.
It should work because.
I can just use the handheld one.
Okay, let me
Yeah.
do it.
Okay, so, all right, so let me first start by talking about the problem that we're trying to solve. So let's say that we have an application, like a banking application, for example, and it has some data that it stores in a database. Now it's going to want to modify or query this data, so it's going to execute some transactions. And it's not going to execute these transactions itself directly on the database representation. It's going to issue these transactions to a database management system, or DBMS. And it's the DBMS that's responsible for updating the underlying database representation and returning to the client application the results of any queries. Now, from the client application perspective, we'd really like that this DBMS is correctly implemented, because if it behaves incorrectly, that means that our application may behave incorrectly. However, in practice, this DBMS may be a black box system, maybe it's proprietary. And so the question is, in a scenario like this, how can we tell if the DBMS is running correctly? So if we think about it, actually, from the client point of view, we don't care that the DBMS is really implemented correctly. We just want it to run our transactions correctly. So in the paper, we define this notion of observational correctness, and I will just give you some intuition for this here. So we assume that we have a set of client-logged observations. These include things like the initial database state, the starting and end times of transactions, the transactions themselves, and the results of any queries. And then observational correctness of the DBMS is then the property that says, does there exist a correct execution of the transactions in this log that is consistent with the observations recorded by the client? If we have this, then we know that the DBMS implementation that gave rise to this log is indistinguishable from a correct one on these transactions. So this is what we want to check. There's currently no way of checking this, or there wasn't, so we decided to come up with a way of doing this. In doing this, we had to contend with some challenges. So the first one that I'll mention is that DBMSs provide different isolation levels, and these govern the extent to which transactions can see the effects of other executing transactions. So for example, one isolation level is serializability. One way of formulating this is that if we have a serializable isolation level, we expect that there exists some order of the transactions such that each transaction reads only from the most recent database state. On the other hand, we can also have a different isolation level, like read committed, in which case the transaction can read from potentially any past database states, and even reads from the same transaction may read from different states. So these are two different isolation levels. In practice, there are more. We'd like to come up with a way of checking observational correctness that is flexible enough to accommodate different isolation levels. The second somewhat related challenge is that if we look at the language used to write transactions, the operations and statements of this language are usually such that their behavior is defined with respect to a particular database state that the transaction can read from. We just saw that transactions can read from potentially many database states, so we can't directly use semantics that's like this. And the final challenge is that of scalability. Scaling becomes harder as we have isolation levels that allow for more and more non-determinism in which states can be read from. And also this becomes challenging as we have higher numbers of transactions and higher complexity of transactions. So I'll talk about each of these. I'm going to start by talking about the second one. So the way that we deal with this is we take our original semantics that is only allowing their transactions to read from a single database state, and we just lift it to a version-aware semantics that allows the transaction to read from sets, any of a set of database states. So the idea for the version-aware semantics is basically that it lets us, as I mentioned, execute transactions with respect to a set of potentially readable states. So we can take an example of maybe we have this transaction that's trying to deposit $100 into the bank account with ID 2. as an example. And if we run this transaction with respect to like the set of two states, then the version-aware semantics will allow us to read from either of them. So this is a non-deterministic semantics. Our version-aware semantics also produces the set of writes performed by the transaction, the result of the final query that you would find in the transaction. In this case, there's nothing, and also read records, which keep track of which states were read from for each read. Now, if we run the transaction according to the version-aware semantics with respect to a set of states di, this is going to take us to a new set of database states di plus 1. And this is just all of the states in di, but with one additional state, which is the result of applying all the writes of this transaction to the latest state in di. So with the version-aware semantics, we can actually check observational semantic correctness. So this isn't full observational correctness. We don't have anything about isolation levels here. But in terms of the semantics of the transactions, we can check something. So the way this works is we can take our initial state from our log, and from this construct our initial set of database states, and then run all the transactions in the log. And then we can use the results in the execution of the semantics. We can use the queries, the query results there, and the query results in the log to construct a set of observational semantic correctness constraints. And if these are satisfied, then we know that the DBMS implementation is observationally correct with respect to this log. If we don't have that they're satisfied, then we don't know. Why? Because, well, remember the semantics is non-deterministic, so there could be a different run of the semantics that does have these constraints satisfied. So what we really want to do is find whether there exists an execution of this semantics that satisfies these constraints. And I'll come back to this later, because first I'd like to talk about the missing ingredient for checking observational correctness. So, which is basically, we've talked about semantics, but what about the isolation level? So we need to make sure that all of the states that were read by the transaction are actually something that is allowed by the isolation level. So the way he handled this is we formulate the conformance to a particular isolation level I as a constraint Ci, and this is parameterized over a set of database states, writes, and read records produced by the semantics. And we have that if the constraint is satisfied, then the execution that produced the database states, writes, and read records was correct. And the nice thing about handling isolation levels like this is that it's easy to define new isolation constraints independently of the semantics. So if we have many different isolation levels, as mentioned earlier, then we can just define some new isolation constraints, and this is independent of how the semantic part is handled. So if we put all of this together, we can start with a log of observations and execute the transactions in the log according to the version-aware semantics. We can use the results of this execution and the recorded query results in the log to formulate semantic correctness constraints. And we can also use these results to formulate these isolation correctness constraints. And if we have that all of the constraints are satisfied, then we know that the DBMS implementation is observationally correct with respect to this log. So the thing is, this is really only looking at a single run of the semantics. It's non-deterministic. We want to see if there exists any execution of this semantics that satisfies these constraints. So one way that we can search for this execution is that we can just encode this entire thing symbolically and give it to an SMT solver. And if the SMT solver says that it's satisfiable, it finds such an execution, then we know that the log is observationally correct, that the DBMS is observationally correct with respect to the log, and otherwise, if it says unsat, we know that it's not observationally correct. There's no execution that is going to give us what we saw in the log. So the question now is, how do we do this encoding? So something we could do is maybe like a bounded model checking style encoding, right? The thing is that this kind of naive encoding scales really, really poorly. So instead, what we do is we define a new semantics. This is a partially symbolic semantics. So what it does is it works over and directly generates partially symbolic representations of sets of database states, reads, like query results, writes and read records. And it also generates constraints on the transaction's execution that need to hold for it to have successfully executed. We can then use these directly to formulate semantic correctness and isolation correctness constraints as SMT formulas, and just conjoin these and give them to the SMT solver. And the rest of it's pretty much works the same way. So I don't think I'll have time to really talk about what's going on in the partially symbolic semantics, but to give you some idea here, this basically is going to work like symbolic execution when it has to, but it will try to, when possible, execute the semantics concretely as much if it can, and also maintain as many values concretely as possible. And by doing this, we can greatly reduce the complexity of the formulas that we end up giving to the SMT solver. So in terms of actual experiments, when we ran some experiments with the naive encoding that I mentioned before, this sort of BMC style encoding versus the constraints we get with this partially symbolic semantics, where the naive encoding gave us formulas that took the SMT solver around 40 minutes to solve. The partially symbolic semantics generated constraints were able to be solved in under 2 seconds. So that was one way that we deal with scalability. Another way that we deal with scalability is by developing a bunch of heuristics. Most of these are helpful. One of them is only helpful for workloads with high non-determinism. I don't think I will have time to talk about them now, so please read the paper. If you have more questions about this later, I'm happy to answer them. So we implemented all of the ideas that I presented so far in a tool called Troubadour, which can be used to audit client-side DBMS logs. Troubadour supports a fragment of MySQL, and depending on the isolation level and the complexity of the transactions, it can scale to handle hundreds or to thousands of transactions in 5 minutes. And we applied Troubadour to an industrial DBMS under development. It was able to check a log of around 1 million banking application transactions in under 2 hours, and a log of 66,000 transactions from the TPCC online transaction processing benchmark in a little over 89 hours. And in applying Troubadour to this system, we were also able to discover 2 previously unknown bugs in the query processor, which was useful and also pretty cool. So I'd like to, at this point, touch really briefly on some future directions that we're currently working on. So one is that we would like to eliminate the need to provide any kind of initial state or set of initial states to enable angelic verification. And the other thing that we'd like to do is eliminate the need to provide any of this timing information about the transactions. Troubadour already supports some ability to explore different orderings of these transactions, but it's not complete, and we'd like to explore better ways of doing this. So that's pretty much all I have to say about this. If there are any questions, I'm ready to take them. Thank you for listening.
Hi. So this looks very exciting. I was wondering if you had any thoughts on whether the same technique could be applied. I'm really hard to hear with the mask on, aren't I? I was wondering if you had any thoughts as to whether the same technique could be applied to conditions like opacity or persistence or the sort of distributed system style consistency that we are working on in other domains.
So I haven't really thought about that too much yet. I do think that a lot of the machinery here can be used to check other kinds of properties. What we were looking at for a little bit was like equivalence of refactorings of transactional workloads under weaker isolation levels, and I think this might be useful there. I haven't thought about what you mentioned specifically, but I could see a lot of this being useful for checking other kinds of things as well.
A quick follow-up. Do you know if the workloads that you are currently able to verify could be verified by the opacity checker community under the opacity conditions, as opposed to, which is just a different kind of transaction condition?
I don't exactly know. So it depends on how I'm not sure how directly applicable this is because of how the isolation constraints are defined. So if it's something that can be defined in this way, then maybe, but I'm not sure.
We'll talk offline.
Yeah.
Unfortunately, I think we run out of time for more questions, but let's thank the speaker again and get the next one plugged in. So we'll shortly be hearing about deadlock detection from Branislav. Exciting AV changes before our eyes are happening.
One, does it work? I don't think it's working.
It's not on yet.
Is it? I'm saying things right now. Oh? Stay closer. Is it better?
No. I think we probably need to give up on that lapel mic. I could give mine to him too. Do you want to switch to this one that's already working, that I'm using right now?
Need to put very close, like this.
Okay, cool. Let's talk about deadlock detection. We got an example here, which it got resolved pretty quickly. So let's say we have a distributed system with many services running around, and they sometimes make blocking calls. That means if they just call another service and just wait for a reply, they do nothing until they receive a response. That yields a sort of like wait-for graph where processes sometimes just begin wait on each other, and it's not a surprise that they would eventually run into deadlocks, such as this one here. And you might find it like sometimes it's quite difficult to spot, you know. And the problem is that that's not just where the problem is, because it escalates. Any service which is locked on a deadlock service also sort of participates in this problem and gets stuck. And it is a quite practical problem. Yeah, like that's a deadlock on my way to my home university in Warsaw. It's not that trivial to also point out who's named. I guess if you remove that bus, everything would get unlocked, but this ambulance down there doesn't seem to be very good name. So, the problem. We want to detect deadlocks in airline-like systems, specifically based on general systems, but we'll get to that. We want to do it in terms of black box monitoring. That means at runtime, we are not interested in this project. We are not interested in static detection for its feasibility. We'll talk about that in later. And without decentralized supervising, so we don't introduce bottlenecks and like a central entity to a distributed system. I would also like to have as little as possible code intervention, ideally none. And you might be like, hey, Radosław, this problem is older than you. It's been solved so many times. Well, we've looked into it, and existing solutions to that are not based on monitoring, first of all, and they're surprisingly informal. The proofs are very often a single paragraph argumentation why the thing works, and they also lack many assumptions. They don't present their assumptions, especially semantics, very rarely I've seen even syntax described, and they don't specify properly invariants. So that's what we are addressing in this project. So we provide distributed deadlock detection via black box monitors. We provide proofs of transparency. We'll get to what it means. provide an algorithm for sound and complete deadlock verdicts, which we implemented for Erlang and Elixir, and we proved its correctness in public. So hopefully there's a discussion about its reliability. Okay, so what we are working on. We are interested in generic servers. Those who know generic servers in Erlang, then this should be clear. But for those who don't know, or more from the formal side, we formalize it as what we call a single-threaded remote procedure call. That's, it can be described as a simple three-state LTS with some additional I/O buffers, which we'll get on the next slide. So each service in this setup begins in a sort of ready state, and it just expects queries from other services to come in. Once the query arrives, the service begins working on it, on a reply to it, and in the meantime, it might call other services. So if it itself sends a query out, it becomes locked and waits for a reply doing something in the meantime. And eventually, when it sends a reply to the client, it becomes ready again and it's ready to pick up further calls. We model such a service operating in this scheme as a triplet of an input queue, output queue, message queue, and the encode state, which we call process, which does this LTS. This is to make it more similar to how Erlang behaves. Like Erlang has message queues, it's a message bus-based archive system. Now, a monitor service in our formalization wraps such a service with additional layer of a monitor queue, like it has a separate input queue. It has a monitor process, which for the record exactly looks like you can see here. It's a perfect depiction of it, which implements the deadlock detecting algorithm. So it oversees the communication going in and out. In other words, if a message arrives into such a monitor system, it lands in the monitor queue, and then it's passed down to the service which is monitored. But also a copy of this message is received by the monitor itself, which can react to it by updating its internal state, but also communicating with other monitors through special messages called proxies. Obviously, the same schema you can see for outgoing messages. So the service sends a message, it also goes, the monitor also gets notified about it and it has a chance to react. So the first thing we want from such a system is transparency. Put in simple words, transparency means that monitoring doesn't change behaviors. It's split into completeness and soundness. Completeness means that if you have a system and you apply monitoring to it, then wherever the unmonitored system, like variant of the system would go, the monitor one can also reach an equivalent state and follow the same behavior. On the other hand, soundness says that if the monitored system reaches some point, it can continue to such a state so that its unmonitored variant would be able to replicate. Once we have that, we can talk about deadlock detection, preciseness. Preciseness is split into completeness and soundness, and as you might guess, completeness says that if there is a deadlock, such as in the picture here, it will be eventually reported. How does it happen? Well, if a monitor of a locked service observes that it received an incoming query, it sends a special probe against the wait for graph. So it sends it towards the one who sent the last query. This message is unique and is propagated along the graph by other monitors. And if it reaches back the monitor who initiated it and it has not observed an incoming response, well, it screams that a deadlock has emerged. And that boils down essentially to cycle detection here, because we have proven that in SRPC-based systems, deadlocks are just equivalent to cycles. Conversely, soundness says that if you are in this situation where one of the monitors is reporting a deadlock, this deadlock is actually real, so just like in this case here. Where the challenges? But the algorithm itself is not rocket science, but like getting to this the conclusion of why it is correct took us some effort, because it has many, many subtleties. For example, if you would send these not be the case that it has a reply to itself. That's impossible. So this invariant guarantees that unmonitored networks has something reachable and feasible state. Then we have two invariants related to monitored networks called lovely KISS and HIC. KISS is knowledge invariant for soundness, which asserts that whatever monitor thinks, that reflects reality. So for example, if the monitor is locked, if the monitor thinks that the service is locked, then it is indeed locked. Or if it reports a deadlock, then the deadlock is real. Conversely, HIC, that's knowledge invariant for completeness, asserts, like guarantees us that monitor's knowledge is sufficient to report all deadlocks. So if there is a deadlock, then either it is being reported or some probe is on its way, which inevitably will lead to detection. And the final part of the challenge is, of course, like to accumulate it and push it through COP, because it never trusts you. We have implemented it and attached to our work as companion artifact. The project is called Didymon, which allows for almost completely seamless application of this algorithm to systems based on generic servers. So we had a talk on Erlang about it, how it actually works. I encourage you to check out the GitHub. We evaluated it for correctness, performance, that we checked its overhead over the network. Spoiler is very low. We can read the paper if you'd like to see more numbers about it. So that's almost about it. So to summarize, we have formalized black box monitors for distributed deadlock detection. We have provided transparency proofs, proofs of precise deadlock verdicts, divided soundness and completeness, and everything has been mechanized in POC, so we are very sure about these results. As for future work, we plan to generalize beyond SRPC and to see how we can adapt this algorithm and other invariants to support more general models. That's it. I'm happy to take any questions from you.
Thank you. I have got two questions. Sofia Drosopoulou, Imperial College. So first question, you said that you have investigated the performance. Do you know, I thought you said so. Do you know how much slower the systems are getting with that performance? Second question, I can imagine that if you add the runtime monitor, the observed deadlocks will differ from those when there are no monitors, because the monitor changes the latency of things, so you might reach configurations that you wouldn't reach otherwise.
So as for the first question, we have measured it by counting messages and where between what types of entities they are. We haven't measured time because that's quite arbitrary how the system is designed. Mostly we counted how many probes are emitted in different deadlocking and non-deadlocking situations. We came up with some optimizations, such as, for example, delayed execution of the algorithm, and taking into consideration that, for example, the monitor is likely going to run on the same Erlang node as the monitor service, so their communication happens exactly without real I/O. As for the second question, your concern is addressed by transparency. So we have proven that monitoring does not add to in practice. It might make some more likely or less likely.
It doesn't add different results, but it definitely adds that that you might deadlock and you would not have deadlock in the original system, and the other way around.
No, that's completely. The possibility is we can discuss that.
So let's do the laptop switch and we can do one more question while that's happening.
Yeah, so while the laptop is switching.
You should start your question or we'll run out of time.
Oh, sorry, this is closely related to the problem of actor garbage collection, which is detecting when an actor can't receive any more messages. Have you looked into that at all? Do you think that this has applications to that space or no? You haven't looked into it, or there's no application? Okay.
Okay, thank you again.
Testing, testing. Is the microphone better? Testing, testing. Can hear clearly? Okay, okay. Okay, can just put it right here. It was like disappear again. Why? I think I tested previously, should be fine. Okay. Okay, we just start.
It's working? Hello, hello? Okay, great. Is this also working? Yes. All right, thanks for being here. My name is Marco Eidas. This is joint work with Joao, Isaac, Patricia, and Peter, and we're all from ETH Zurich. So the topic of the talk is modular reasoning about global variables and their initialization, and I'll give you an example of what we mean by that. So here's a Java program. We have a class byte that has a static field called cache. So this is Java's version of a global variable. And now what's also in this class is this static block. So that's an initializer block that, if you look at what it does, it allocates an array and allocates a bunch of byte instances and places it in the array. And now this initialization block in Java runs lazily. So what that means is at runtime, if I run this client code at the bottom, for example, the moment I first use the byte class in any way, for example, I read this cache field here, at runtime, trying to read this field will trigger the initialization of the class. So that means I will actually jump in my execution to this initializer block. It will run until completion. At the end, we return, and then we actually perform a field read, and we get the array that was just allocated. So this is a typical use case of initialization of global state and static initialization in Java. This code actually exists basically like that in the standard library. And generally, like typically, global variables and code related to it is a small part of a code base. But of course, if you have any substantial amount of code, probably you're using it somewhere. So if you want to verify your code, you have to be able to reason about it. So this was a Java example, but of course, other languages have similar concepts, whether they're called static fields or global variables in C, C++, and Go. Roughly, we have two big groups. Those where initialization happens lazily, like in Java. That's also the case in C# and Scala, for example. Or those where initialization happens eagerly. So these initializers run before the main function is called, which is the case in C, C++, Go, and others. What these have in common is that reasoning about when the initialization happens is quite difficult. So in the left group, that's the case because this initialization order is actually determined dynamically, right? Because it happens on the first access to the class. But it's also difficult in the right group because in all those languages, the order in which initializers run actually depends on the compilation order. So on the order in which you pass different files to your compiler. So that means in all these cases, the initialization order and the exact time on which initializers run is not known modularly. So if you implement a library that uses static code, you do not know exactly when and in what order your initialization code will run. So our goal in this paper is to solve this problem and to find a way to do modular language-independent reasoning. So reasoning that works for all of the languages that I've mentioned before, whether lazy or eager, about global state and its initialization in the setting of concurrent separation logic. And our basic approach, our central kind of specification instrument, is what we call module invariance. So what a module is depends on the language. In Java, it would be a class. In Go, it would be a package, and C, a compilation unit. But the point is that a module invariant describes valid states of your global state. So if we go back to the byte class, we want, as a first constraint, that the initializer always has to establish the module invariant. In the byte class, we would say, well, the cache field can't be null, and the array has a specific size, and it contains the right values. Right? So we have, as a first proof obligation, that the initializer has to establish this invariant. It has to hold at the end. And now the second and super central aspect is that clients should be able to use this invariant without having to reason about when exactly initialization happened. So as I've just said, doing that modularly is very difficult or impossible in these languages. So if a client wants to use an invariant, it shouldn't have to reason about when exactly initialization happened. Instead, it should prove some set of sufficient conditions that together imply that the invariant must be holding at this moment, no matter when exactly initialization has happened before. So if I have a client like this, I want to prove some set of proof obligations that together imply that the invariant holds now. And then the key challenge is, of course, well, what are these proof obligations? When exactly is the invariant of some module guaranteed to hold? And this is what I'll answer in the rest of this talk. So At a basic level, we have two central proof obligations, right? We know that an invariant of a module will hold if the initialization of that module has finished, so the invariant has been established, and also the invariant is not currently broken by someone else. But as I've already said, proving this left condition modularly is really, really difficult. So a central contribution of the paper is that we've identified two other conditions that together imply that the initialization has finished, that we can actually prove modularly. And those are these two. So we proved that initialization of a module must have started at some point in the past, and that the initialization of the module is not currently ongoing. These are two conditions that we can prove modularly, and I'll show you how in a second. And together they imply that the initialization of a module must have finished. So those three will be our central proof obligations, and I'll walk you through those. So the first one is we must prove that the initialization of a module has started at some point if we want to use its invariant. So if we go back to the same example as before, and this is actually super easy to prove. If we want to verify our client here, we can prove that initialization of the byte module must have started at the point where we try to read the cache field because we're trying to read the cache field. Right, so if we're in a lazy language like Java, then trying to read the cache field is actually what will trigger initialization if it hasn't happened before. If, on the other hand, we're in an eager language like C, then initialization will have happened long ago before main was even called, right? But in either of these cases, we know that at the latest, when we try to read the cache field, it will have started. And we represent this fact through an assertion that we call an init fact. So init m of a module means at some point in the past, initialization of m has started. So this is the first thing you have to prove if you want to use a module invariant. The second one is what I've mentioned, initialization is not currently ongoing. So concretely, what we have to prevent is this scenario. So it's the same byte class as before and the same client as before, but we have on one additional line. So now from the initializer of the byte class, we actually call the client. And if you think about what happens in this scenario, if we execute this, right, the client will be invoked, but at this point, the invariant hasn't been established, the cache field is still null, and this will actually crash. So in this scenario, it would be wrong to assume that the invariant holds here because it doesn't yet. So this is what we need to prevent. And our way of doing this is a system of what we call initialization levels. So initialization levels are values from some partial order. Here I'm using natural numbers that are associated with every module, every initializer, every method, every procedure. And now these levels have to satisfy some constraints that we can check modularly. So the first one is every module's level has to be greater than that of its initializer. Then we have general rules that ensure that if, for example, we have a client, the level can only decrease with calls. It can never increase with calls. So if we have this potentially dangerous call here to the client method from the initializer, then that introduces a constraint that the initializer's level has to be greater or equal to the level of the method that we're calling. So so far, the levels that I wrote there satisfy all these constraints. And what these two constraints give us is essentially that whenever our current level is greater than that of a module, it can't possibly be initializing. Right? Any execution starting from the initializer will have a level lower than that of the initializer. So that means now in the client, if we want to use the invariant of the byte module, we can show that initialization, or try to show that initialization isn't currently ongoing by showing that our level is greater than that of the module. And this constraint doesn't hold here because we're actually being called during initialization. And this is why we would reject this example here. OK. So this overall system gives us a second proof obligation. Our current level must be greater than that of the level whose invariant we're trying to use. Then we have the last proof obligation, which is that the invariant is not currently broken by someone else. And it could be currently broken by someone else in essentially two different ways. First of all, it could be broken by another initializer, right? We could have this disrupt module here that has nothing better to do than set our cache field back to null. So we prevent this by generally controlling side effects of initializers. Because we're in a separation logic setting, we're just doing this via ownership. So when we verify module initializers, we prove that they're correct in a setting where they only have ownership of their own global variables. So the disrupt module here, its initializer is only allowed to access its own global variables, of which there aren't any. And the byte module's initializer is only allowed to access its cache field and no other global variables. And that rules out this disrupt class here. And then there's a second way that the invariant could currently be broken, and that's not broken by some initializer, but just by other code. For example, we could have this client caller here that calls our client in a state where the invariant is temporarily broken. So again, in the client here, it would be wrong to assume that the invariant holds. So for this final problem, we introduce a notion that we call module tokens. So that's a separation logic resource that essentially represents the right to use the invariant of a module at the current point. So initially, these are all given to the main function, and the main function can then pass them around in the program. So if I finally want to verify my client code here, what I would have to do is first of all give it a precondition that says, if you want to call this, you have to give me the token for the byte class. And now I have the init fact for the byte class, I satisfy the level constraint, and I have the token, and these three things together, I can now exchange for the invariant of the byte class. And that now gives me ownership of the cache field and tells me that the field is not null and contains the right amount of values, etc. So now I can read the field, I can change it if I want to, I can exchange the invariant back for the token afterwards if I want to. Okay, so that's the basic idea. In the paper, there are more things. So we have a notion of duplicable module invariants that are never broken after they're established. For those, we don't need the token. They're useful for read-only state. We also talk about solving a different problem, which is initialization cycles that I haven't mentioned here. We formalized this whole thing as a concurrent separation logic based on Iris and proved it sound in Rock. The formalization is quite interesting. If you like this kind of stuff, you should have a look. We've implemented the technique in 2 different SMT-based verifiers, in Vercor for Java, which is lazy initialization, and in Gobra for Go, which is eager initialization, and verified a bunch of small case studies. And arguably more importantly, we've integrated this technique into a larger verification effort of real-world Go code base. So this is 5,000 lines of Go code that constitute a router implementation verified in Gobra, and that uses global state, and where previously essentially there were unjustified assumptions, now we use our techniques to have sound reasoning about this global state. So, to conclude, I showed you the first modular verification technique for global variable initialization. It's based on concurrent separation logic, applies to a wide range of languages because we abstract over the exact initialization time and semantics. We proved it sound in Iris, implemented it in Vercor and Gobra, and of course all of this is in the artifact, and you can check it out if you want to. Thank you.
Do we have any questions?
So the technique is language agnostic, and you can use exactly the same verification conditions in a lazy language and in an eager language. So there's one logic that works for both, because we're only making like a set of very basic assumptions that are true both in the lazy and in the eager languages. Like that, for example, initialization starts at the latest when I read the field, right? That's true in C and in Java. But in the implementations in Vercor and in Gobra, we actually incorporated some additional knowledge, right? Java does give additional guarantees beyond our basic assumption, and so does Go. And so there we can actually skip some proof obligations that exist in the logic because we know from the language that they're always true, or we just have additional guarantees from the language. So there's one base logic that covers all the cases, but then you can incorporate additional language-specific like knowledge if you want to.
Let's do the laptop switch here. Was that another question? Okay. Pick your favorite.
Well, the thing is initialized if its initializer has started and is no longer ongoing, right? That's those two things combined to it must have finished. Because those two things are things that you can actually prove modularly, right? The starter thing is easy to establish, and the not ongoing follows from the levels on the call graph. It turns out that like directly proving it's finished is just really, really hard. So this was a way that, in a modular way, right? Modularity is the key issue. So like essentially picking it apart into these two separate proof obligations was what enabled to do it modularly. You can treat them like that, yes.
Thank you.
以试一下，现在我们开了。
可以可以。
Neural network. Today, this session, we have 7 talks. The first talk is by Zhonghui Ma from the University of Queensland. He's going to talk about convex Hall approximation.
Okay, hi. Hi, everyone. My name is Zhonghui Ma from the University of Queensland.
Today, I will present our work, convex Hall approximation for activation functions. This is joint work with Zihan Wang and Professor Guangdong Bai. Neural networks are now fundamental in vision, language, and control systems. For example, traffic sign recognition and robot control system. They are powerful, but this wide usage also raises reliability concerns. In safety-critical domains like aviation and autonomous driving, we need neural networks to be 100% correct, even under small perturbations. This is why verification matters to ensure robustness formally. Here is an example. In the picture, this is the ARCAS XU artifact collision avoidance network, a classical verification benchmark. So what is neural network verification? Neural network verification checks whether a model always behaves as expected. Formally, for all inputs in a region, the outputs must in a safe region. So it's about proving the network is always correct under certain inputs. Next, what to verify? A common goal is local robustness. Small input changes shouldn't flip the prediction. We test if all perturbed samples within an epsilon ball are classified the same. This ensures the model is stable to tiny noise. So how to verify neural networks? The main idea is that we estimate output ranges based on bounded input ranges. If our estimated range fully contains all true outputs, it's sound. Exact matches give complete verification. However, there are some challenges because there are non-enumerable perturbations and nonlinear activation functions. So we need to handle this by building linear constraints that describe all variables. Then we infer safe output bounds symbolically. This picture shows different mainstreamed methods on neural networks verification. Different methods trade off precision and efficiency. For example, MILP-based methods are exact but very slow. Relaxation-based methods are fast, but they are not always precise enough. So recent work like Prima and Railu here, they utilize multi-neuron constraints. These methods proposed an idea to construct some non-trivial constraints for neural network verification. Most verifiers use single neuron constraints. They are only about one activation functions with one input and one output. But tighter bounds need multi-neuron constraints across several neurons. It means we will consider multi-neuron at the same time with multiple inputs and multiple outputs. Our work focuses on making these higher dimensional halls efficient to compute multi-neuron constraints. In this work, we aim to over-approximate the convex hall of general nonlinear activation functions because there is another work has contributions to over approximate the convex hull for ReLU functions, and this work we aims to handle the cases of the other activation functions. For example, we handle 3 categories. The first one is ReLU-like functions, like ReLU, leaky ReLU, or eLU. And the second one is that S-shape functions. They include sigmoid and tanh functions. And the third one is multivariable functions like maxpool. They have multiple inputs. And this work proposed a method called ReAct. It means wrapping the activation function whole. First, we give the problem formulation. We take as input a convex polytope region, typically given in constraint form. Our output is another polytope, also in constraints, that covers all pairs of input and outputs. In simple words, we want a convex wrapper around the function's true nonlinear surface. Like in these pictures, showing the examples of ReLU surface and ReLU hull, and tanh surface and its hull. In summary, we approximate each activation function host using double linear piece functions. We also call them DLP functions in the following sections. So they only have simple 2-segment linear curve ways that let us convert the nonlinear function into something almost like a ReLU, much easier to handle. In these pictures, the green surface is DLP functions. Specifically, the step 1 is to construct DLP functions as bounds for an activation functions. We position the inflection point carefully. It means here in a 3D view, the inflection point is a line. We position the inflection point carefully, ensure both soundness and tightness. This replaces the complex nonlinear function, the right surface, with 2 simple linear segments. Like in this picture, we use 2 DLP functions. One is as the upper bound, and another one is for the lower bound. The step 2 is to over-approximate the convex hulls of DLP functions, shown here in the blue one. This step is efficient because we reuse the machinery of our earlier method ReLU, designed for ReLU functions. So by this way, we can construct we can handle the simpler DLP functions rather than the complex original activation functions. And this way is very fast and efficient. The step 3, finally, we extract the active linear pieces, the blue patches. It means we need to choose some useful constraints or sound constraints for the convex hull of the original function. This gives us the final convex hull that tightly covers the activation function. Depending on the output sign, we know which constraints to keep, because one DLP function is for the upper bound and the other one is for the lower bound. So we can easily choose the correct constraints obtained before. The above example shows the case of time h functions. For ReLU-like functions, the precise simplifies. They are almost convex already. So one DLP bound is enough. Similarly, for max pool, all inputs are non-negative, so we can use some inequality to construct the function hull. Overall, our method has been extended to multiple activation functions, and it's very efficient and effective. For the evaluations, the first part is to compare our method with the SODA convex hull over approximation method. From the figure, we can see that our method is more efficient and precise. Also, we need fewer constraints. Next, we implemented our method into the neural network verification framework. This is about local robustness verification, and you can see that in these figures, we can obtain more verified samples with less runtime. Thank you for listening. Welcome. Any questions?
Hey, thanks for the talk. I wonder why did not you compare to alpha beta crown, which is the state of the art now in verification? Did you consider comparing to it?
Sorry, consider what?
To alpha beta crown.
Yeah, alpha beta crown.
Yeah, the state of the art in verification.
Okay, alpha beta crown is a very classical method, and it focuses on single neuron constraints. So this is where it's different from our method. We consider multi-neuron constraints.
Okay, thank you.
Thank you. But we also compare the alpha crown. Yeah, yeah, you can see the specific results in our paper, maybe.
Okay, let's thank the speaker again.
Can I start 30 seconds early?
If you want to wait for more audience,
Sure.
Okay, our second speaker is Anastasia Izichev from TU Wien. She's going to talk to us about mixed precision tuning.
Okay, thank you. Thank you so much. I haven't even started yet. All right, so today I'm going to talk about the cost of soundness in mixed precision tuning, but first let me clarify what mixed precision tuning is. So it is a performance optimization designed specifically for numerical programs, and what it does, it assigns potentially different finite precision types to variables and arithmetic operations. And it is based on the observation that operations performed with fewer bits in low precision are generally faster than the same operations performed in higher precision, but they have lower accuracy. And secondly, different operations inside one expression contribute differently to the overall accuracy of this expression. So what the tuner needs to do, it has to navigate the accuracy performance trade-off, and unfortunately, all the potential precision assignments are not, it's not a smooth function. So there might be jumps in accuracy and in performance. So what the tuner is trying to do, it is trying to assign the lowest possible precision assignment that satisfies some user-defined accuracy constraint. Let me show you an example. Say you have an algorithm. The details of the algorithm here are not important, but say you want to implement it accurate up to 10 to the power of minus 16. So as a developer, what are your options? You could use very high precision, say 128 bits or quad precision, and assign it uniformly to all operations, and then executing such a small code snippet on 1 million samples would already take 5 seconds. But of course, it satisfies your accuracy constraint. Actually, it overly satisfies it, overshoots it by 18 orders of magnitude. So if this is too slow for you and too accurate, what can you do? If you just have uniform precision assignment, you can go to 64 bits or double floating point, and then such a code snippet, again on the 1 million samples, would run much faster. It's way under 1 second, but it doesn't satisfy the accuracy constraint that you had initially. So what can you do? What mixed precision tuning would do is you can keep all of the operations in high precision except one and downgrade it to double floating point precision. And such an implementation would satisfy the accuracy constraint and actually quite closely. And also it would run 10% faster than the original uniform quad precision. So this is just to give you an idea what this optimization is doing. And the tuners that do such optimizations can be classified in two big conceptually different groups that differ based on how they estimate accuracy of the generated programs. And on one side, you have sound static tuners that use sound static analysis to compute the worst case rounding errors of a program. And they provide guarantees because they generate, so they talk about worst case scenario, but because of that, they are also overly conservative. On the other side of the spectrum, we have dynamic tuners that use sampled values to reason about rounding errors. And because of that, they do not provide any guarantees since they are not sampling all possible values. But this also enables them to be more aggressive in the way they are optimizing the programs, which potentially might be beneficial. And there are multiple tools in each of the groups, and there are comparisons and evaluations of within each of the groups. But the question remains, how do these two conceptually different groups of tuners compare? And the hypothesis is that sound static optimizers are inherently slower and less effective than the unsound dynamic ones. The question we wanted to ask is by how much exactly? So if the user wants soundness guarantees, basically what is the cost attached to such a choice? And how to answer this question? First, we needed to find the common ground on which both types of tools can be evaluated. So we have reference points for direct comparison. And we needed to find a meaningful metric that will quantify effectiveness of the tuners. So for common ground, we started off with the FEBench standard benchmark set that is generally used for assessing quality of numerical analyzers and optimizers. But some of these benchmarks actually contain loops and conditionals, and currently none of the static tuners can handle such control flow constraints, control flow statements, without any pre-processing. So there would be no reference point for static tools, which is why we had to exclude them, and we only compare on the straight line code. And another important point, as a part of the specification, we have these accuracy constraints, And the effectiveness of the optimization also depends on this part of the specification. It was previously shown that the most effective optimization can be done if the constraint, if this error budget, is just below what the uniform precision can provide. So we came up with 3 different scaling factors, and we took as a reference value what the analyzers, the tuners, reported for uniform double precision for each benchmark, and then we scaled it down to obtain different specifications. For effectiveness, we essentially needed the metric that would tell us how well the tuner can navigate this accuracy-performance trade-off. And because we are comparing sound and unsound tools, we called this metric cost of soundness. And it has multiple components. For each optimized program, we first evaluate the performance improvement in terms of speed up in running time of the optimized program P prime compared to the original high precision program P. For accuracy, it was a little bit more tricky because just comparing the difference of the accuracy, the increase of the error, is not meaningful because it varies a lot across different benchmarks. And additionally, conceptually, the tools, these 2 different groups of tools, optimize with respect to different reference implementations. So sound tuners optimize with respect to real valued ideal implementation that doesn't have any error in it. And dynamic tools usually run some kind of high precision implementation and use that as a reference to optimize further. So as the accuracy metric, instead of just computing the increase of the error, we are assessing how well the tuner can use the allocated budget of the error. So basically within the budget that we, or the user, gave to the tuner, how much of this budget is used in order to improve performance. And we combine these 2 metrics into this cost of soundness combined metric, where we give higher weight for performance because mixed precision tuning is a performance optimization. And we normalize this use of budget to essentially equally punish the programs that violate accuracy constraints, so they overshoot the budget, and the ones that do not use the budget at all. And for this comparison, we focused only on the tuners that operate on floating point precisions, either IEEE or arbitrary ones. And among those that were available open source, there were 2 standalone static tools, FPTuner and Daisy, and the meta optimization Regina that can be combined with any static tool. So for dynamic tuners, there were only standalone tools, and we compare with them. I will show you results only for one of the error budgets, but actually results look similar. The trends are similar for other budgets as well. So what's going on this graph? Here on the x-axis, we have the 100 benchmarks sorted. And on the y-axis, I have this abstract cost of soundness metric that I explained to you. So higher values here mean better. So basically, the red curve of the triangles is the best, most effective tuner. And I don't know how well you can see the size of the font, but actually the most effective tuner is the combination of a sound tuner with regime inference. So what regime inference is, in a nutshell, it subdivides the input space for a program into multiple subdomains and optimizes each of these subdomains separately. So what this result actually tells us is that the soundness does not inherently come with a cost. And if you enhance sound tools, sound optimizers with some additional algorithms like regime inference, you can, without sacrificing accuracy guarantees, you can also outperform dynamic tuners. For standalone tools, the picture was slightly different, and as expected, they were, in fact, static tools were in fact much less effective than dynamic ones. And there was also a pronounced drop in effectiveness when we decreased the error budget. For dynamic tuners, we also observed this drop in effectiveness, but it was not as steep across different targets, and it happened mostly because the optimized programs violated the accuracy constraints more often and on more benchmarks. In terms of optimization time, there was a clear winner that optimized programs way below half of a second, and there was the slowest technique that was a combination of this regime inference that repeatedly calls sound tuners on different parts of the input space. But otherwise, we were surprised to see that there was no clear trend that sound tuners were either slower or faster than the dynamic ones. So let's revisit our hypothesis. We now know that, in fact, sound tuners are not inherently slower than the dynamic ones, and they are less effective if we are talking about the standalone tools, but recent developments in meta-optimizations allow sound tools to compete and actually be more effective than dynamic ones. So what I would like you to remember from this talk is that the goal of the study was to quantify the difference in effectiveness between sound static and unsound dynamic mixed precision tuners. And on simple programs, we concluded that soundness does not inherently come with a cost, which was a really pleasing result for us. But of course, there is a caveat that on complex programs that contain control flow, dynamic tuners remain, for now, the only choice. So this result, we don't know yet if it will generalize. The static tools are not there yet. Thank you for your attention.
In machine learning, you do very different type of lot more small precision parts, and also things, even though there's loops, they can be a lot more statically countable. So can you apply some of these techniques to like machine learning kernels?
I mean, that depends, of course, on what kind of loops, right? So say if in embedded systems, they also use a lot of these loops, but if you read a fresh set of values every time, and there is no rounding error that would propagate from iteration to iteration, then it's the same as if you don't have a loop. So for this scenario, for sure, you can apply it as is. And for other scenarios, you can try dynamic ones, but then, again, the accuracy guarantees are out of the window.
Thank you for the talk. I wonder how we can use your method to get a scheme, a quantization scheme efficiently, more efficient quantization scheme. Did you think about that? You compare methods, but
yes.
Can you create methods?
Well, that was not the goal of this particular study. Of course, there are different, so there is research in this area, yes. That was not the goal of this study.
Okay, so you see that, you can see that your approach can be, for example, integrated in some training method for neural network or something like that, to make a quantization more efficient after that.
Yes, for sure. That, I mean, I wouldn't be able to name the papers on the top of my head, but yes, people apply mixed precision tuning in context of machine learning as well.
Okay, thank you.
Thank you.
Okay. Our next speaker is Willow Arendt from Georgia Tech. She's going to talk about Finch and tensor programming.
Halfway across the world because I'm obsessed with arrays and I want to talk about it. Array programming is really productive. Oftentimes we see array programming with things like collections of collective operators like plus or times and numpy. Sometimes we see array programming with these ein-sum interfaces, kind of generalizing this concept so that you can have any pointwise expression on the right-hand side and it sums over the indices. These frameworks have really shaped how we think about productive programming with collections of data. And array programming is a really core concept for computer science. It's one of the first data structures that we teach. It's in many programming languages. The semantics of arrays are roughly the same everywhere. And these frameworks are really well implemented. They're pretty fast. We're reaching peak machine throughput for a lot of these systems. But one thing about these frameworks where they fall short is that they really only represent dense arrays. Data in the real world has structure beyond this dense rectilinear grids of data. In scientific computing, we often see these triangular matrices. So this arises when you're doing a solver and maybe you only store the upper triangle. We might see a banded matrix, something like a symmetric matrix. Scientific computing also gives rise to sparse matrices. So in this example, perhaps this sparse matrix is representing this triangular mesh. So the rows are triangles and the columns are triangles they might be connected to, and we say that a non-zero represents one of these connections. In domains like machine learning or quantum computing or finite element methods, we may see different kinds of patterns of sparsity where the non-zeros occur together. This is an opportunity for further optimization. Additionally, of course, in machine learning, we might do a convolution. I'm a compiler writer, so I don't like to support this I minus j kind of thing, especially on my sparse arrays. But one interesting thing is we can recast operations as structure sometimes. So in this case, if we wanted to represent convolution, we might recast this I minus j as a matrix of circular shifts of the filter. And now convolution has become matrix multiply, and I'm happy again. Of course, if we're doing convolution, we might want to pad the matrix, and padding is yet another kind of structure. And moving on from just sparsity, we might see structures that represent something like repeated data. So in this case, instead of storing redundant adjacent pixel values, we'll store the color of the pixel once together with the number of times it occurs. This is a really useful optimization in something like a computer-generated image, like a screenshot. We also see run-length encoding occur in databases. If you're doing a column store and your entries are sorted, you might see adjacent values that are the same. So here we can annotate some of those runs and use run-length encoding to store the columns. So there's a lot of different structures that we might see, and supporting this structure is really challenging. It was easy in the dense case because dense systems have this property where they're kind of self-similar from the theory all the way down to the hardware and the systolic arrays. It's all rectangles all the way down. Critically, the relationship between where entries are represented in theory and where they're stored in memory has a really clear correspondence with like this row major one-to-one relationship. Whereas when you have something like a sparse tensor, this relationship is broken. So if I was talking about this adjacency matrix where we have triangles connected to triangles, triangles only have 3 sides. So there's a maximum of 3 non-zeros in each row. This means that we should probably only store just the non-zeros. Storing the entire matrix would be an asymptotic overhead, and on some systems it wouldn't be feasible. So another optimization that we might want to do is that we actually may want to modify the computation itself to match this storage optimization. So we may want to avoid multiplication by 0, for example, because x times 0 is equal to 0. So we really only want to process these elements. If we stored them using a standard format like compressed sparse column, we might store an array here. Val is the non-zeros. IDX might be the locations of the non-zeros within each column. And PTR is going to be the delineation between columns. So we see that the relationship now between where they're stored in theory and where they're stored in memory becomes quite complex. Existing compilers tend to restrict the control flow that they support so that they can handle these more complex structures. So oftentimes they'll still use these high-level collectives to express a more constrained version of an input program, and then they'll use scheduling languages to express a restricted set of optimizations that they do support. Something like compute at to use a temporary, they might reorder or split loops. or add some pre-computation, and you can have different schedules for different situations. So we can kind of characterize this trade-off between program flexibility and array flexibility with this feature matrix. Halide is a very popular dense compiler. It supports only dense arrays, but it supports a really wide variety of control flow constructs on those arrays. Taco supports combinations of dense and sparse arrays, but at the cost of some kind of control flow features. We see a sort of proliferation of different compilers for different kinds of structure. So this Cora compiler, for example, is a compiler for ragged arrays. There's a trick that you can do to support more kinds of control flow. If you restrict your attention to only one structured input, you can kind of use that, the structure of that input to guide the execution of the program through the control flow. So that's a trick that Tai Chi uses to support a much wider set of programming constructs. But of course, in this talk, we will show you how you can have both. So to give an overview of the kind of system that we're building, we're going to allow you to express high-level control flow directly with loops. And then we'll have a parameterized format description language that allows you to express a wide variety of formats for different use cases. They'll be combined with our compiler, and they'll produce efficient executable code that only stores and processes the non-zeros. Starting with the control flow, let's take a simple example where maybe we'd like to do a dot product on only the even values of two arrays. So you might write that in the Finch language like this, where we declare the output as 0, and then we sum up these pairwise products if they're even. And that would lead to a little bit of output pseudocode that iterates over the intersection of A and B, and then if the index is 0, then it adds it to this sum. Of course, if there may be different situations depending on the sparsity of the inputs that you may want to take different approaches. If A is a very small list of non-zeros, then maybe we want to filter that first. So the idea here would be that we only find the even values of A, and then we can go ahead and do that dot product. So this is how we would write that at a high level in Finch. And then the Finch compiler goes ahead and automatically generates some code that looks like this. So here we can see we iterate over the non-zeros of A, and then we do the intersection. And then, of course, maybe we want to do the intersection first, the filtering after. That might look like this. And you can see that each of these strategies may be better or worse in different situations. So being able to express different control flow is really important for the performance of the program. I'll move on from talking about the control flow language to the language of structures. And we sort of took a bottom-up approach here where we asked what kind of structural properties are important to support. So, is it sparse? Does there have a background value? Are the features actually contiguous? Are the features repeated? Do you have several contiguous homogeneous features? And then, of course, if there's only one feature in every row, then maybe we can avoid emitting a loop for that particular dimension. And so we sort of take the Cartesian product of all of these properties, and we come up with a wide variety of these one-dimensional formats. And then we can nest the one-dimensional formats to produce this parameterized language of different structures that we can express in Finch. I know that this is a very complicated diagram. I'll give you my favorite. I think if you nest an interval structure with an interval structure, you have a very cute little bounding box here. So this is a wide variety of features that we can represent. Now, the trick is combining control flow and data structures in the same program. So to do this, we introduce a notion of scopes. We have our declaration statements with this dot equals syntax. And we're going to restrict tensors to have only two modes, readable and writable. This allows us to construct the tensors efficiently. And then when we change between modes, between writable and readable, we have a few core interface functions that each of these structures needs to implement. So we'll call the freeze function here, and then if we transition from reading to writing, we'll call the thaw function. We restrict tensors to only change their modes in the defining scope. And this is what allows us to treat the tensors as constant when they're on the right-hand side and use this looplet concept to lower an individual loop. So this is a prior work that sort of represents a rewriting-based progressive lowering strategy to tackle the one-dimensional case. I'll give a little case study here. If we wanted to implement breadth-first search in Finch, we can talk about what kind of optimizations are required, and then how we would implement that. So the core idea of breadth-first search is that if we represent the frontier of nodes that we're currently visiting in a one-hot encoding, then we can say a vertex should be added to the next frontier if we haven't visited it yet, and one of its neighbors is in the current frontier. So that's what this equation is saying. Row major approach would be a really standard way to do this. You might represent this operation as a row major matrix vector multiply. But there's a few optimizations we can do. So if we iterate column major instead, then we can restrict our iteration to only visit nodes that are currently in the frontier. This is kind of a straightforward approach. But one thing you may notice is that if we're in the row major paradigm, then we can use the set of vertices we haven't visited yet as a filter instead. So you have a choice between these two different filters. Furthermore, if we're in this row major pole-based traversal, you can also use short circuiting, right? It doesn't matter how many neighbors are in the previous frontier that you're adjacent to. You just need one. So as soon as you find one, you can stop. Then there's a few structural optimizations you might do, which I don't have a very cute image for, but if the edges have weights, for example, you might represent a structure that only has the pattern of the matrix rather than the weights as well, and then you can simplify the code. You might also fuse the calculation of the parents together with the calculation of the next frontier. So that's another optimization you can do. And here it is in Finch, push and pull traversals for breadth-first search. There's a few features I'll point out here. We have our declaration of all of the structured inputs. We have two different loop orders. So the push traversal is the column major, and the pull traversal is the row major. We have conditional masks, which are masking off based on which vertices we've visited. And we have fused statements, so we can fuse the calculation of parents together with the calculation of the frontier. We represent short circuiting as a structural property. It's an odd choice, but this helps us integrate the effects of break with other structures in the program. So we chose to do this as a structural property of the input. And we see here the performance is competitive with the state of the art. So the red line is GraphPLAS. Both of them represent a speed up over Julia's default graph algorithm. Finally, I'll say Finch is an extensible system. This was accepted in the round 1 of OOPSLA, but we have several works that build on Finch using this kind of, using our control flow interface to precisely describe what kind of iteration and data flow is needed to do things efficiently. So one example here is we had a compiler called SysTech, which generated symmetric optimized code for sparse inputs. So the way that this worked is that it used the control flow constructs of Finch to emit things like filters that only iterate over one triangle of the symmetric input. Another effort that we have going on is that we had a database query optimizer used to actually optimize high-level API calls down into Finch calls at the lower level. And so this was an instance where being very precise about the data flow and the control flow that you emit was really useful. And in the next talk, well, the next talk, you'll see my colleague Jayan describe a system that uses Finch to iterate over continuous values. So we kind of pun on what values an array can be indexed by to allow it to be indexed by real values. So with that, I will take any questions that you have, and we'll go on to the next speaker.
We have time for a very quick question.
We'll do the next speaker.
Yeah, so if you have any more questions, due to the sake of time, we have to stop now. But if you have any other questions, please talk to the speaker afterwards.
I'm here all week.
So our next speaker is Peng Yuan from Ant Group. He's going to talk about meta kernel.
Good evening. I'm Yuan Peng from Antglobe. My topic is metal kernel, enabling efficient encrypted neural network inference through unified MVM and convolution. Here, MVM means matrix vector multiplication. Here is the outline we will take today. We will start with the background on FHE and the motivation by MVM example, introducing our core insight, the fundamental computation pattern in the FHE we call IMLR. Then I will introduce metal kernel, our composition-based compiler built around the IMLR pattern. We will demonstrate how metal kernel unifies the MVM and convolution in the FHE. Finally, we will look at the evaluation result. FHE is the encryption schema that supports computation on the ciphertext. For example, we send the encrypted image, a tensor of the cat image, into the cloud, and the cloud performs the model inference with the ciphertext input, or the operator compute with the ciphertext, and the result is also the ciphertext. Only the client can decrypt the ciphertext to get the result. Here is the FHE software stack. The core of FHE is the schema, including CKKS, BFV, and TFHE. Several libraries such as OpenFHE, C, and Latigo provide the CKKS primitive to the developer. And many chips such as CPU with AVX, GPU, and special FHE accelerator accelerate the FHE schema. For the AI model, we need the domain library and compiler. So metakernel is in the domain library and compiler level. Programming FHE is hard. We start with the CKKS to see the data types and operation. The data type is ciphertext. We can think ciphertext as a huge vector of float elements. Each ciphertext can support 32 or 64 kilometer float element inside it. So patching tensor data into the ciphertext is hard. There are restricted operations on the ciphertext. For the CKKS, only addition, multiplication, and rotation are supported, and the rotation is the most costly in these three operations. So reducing the number of rotation is very important. So our work tries to answer the question, what is a good programming abstraction for the CKKS for the AI model? For the CPU CMD, the automatic vectorization is very popular in the compiler. And for the GPU tensor core, we have several abstractions such as the Catalyst template, Triton compiler, and QDN. How about the CKKS for the AI model? We start with a simple MVM example to see how the CKKS work. This is a 2x2 matrix multiplied with A. First, we implement the MVM with dialog method. For the matrix B, it is transformed into D, which is the dialog layout. For example, the 1 and the 4 are in the first row of the D, and 2 and 3 are the second row of D. And each row of D multiply with rotated A to get the final result. For the first multiply, the 5 and 6, and the second multiply, it is rotated by 1 to get 6 and 5. So in CKKS, both A and B are encoding in the ciphertext. You can think it's a huge vector, and then perform the multiplication, rotation, and addition. So the challenge, the programming challenge is data patching. We need to try to maximize the slot utilization, and we also need to control the number of the rotation. For the dialog method, each row needs a rotation, and the output tensor layout is also important because the following operator in the AI model needs the same input layout. Existing compiler try to use full replication to maximize the slot utilization. They try to pack as more as element into the ciphertext, resulting in more rotation because of the summary, and the resulting ciphertext C is not consistent with the input. For example, the input A layout is 0, 1, 2, 3, and the output C is not consistent. Recall the method of dialog. Each row needs a rotation of A. The first insight, can we shift the rotation of A at runtime into the rotation of D at compile time? We use different color to show the position of element in the matrix. We can rotate D into M to shift the rotation into the compile time. And we can continue block the matrix M to reduce the rotation. For example, we can block the first row of M into MB, and then we reduce the number of rotation from the low level into the block level. We can pack the row of M horizon batching to utilize the slot. But we need a reduction to get the final result of C. Okay. Thus, we get the Imler pattern, which can represent the initial computation without blocking, the vertical blocking, and horizon batching in the same formula with some parameter such as the batching size and the horizon size. And the important factor of the formula is each metal kernel only needs one rotation, so help us to build a cost model. After we get the Imler pattern, we can found a cost model. The formula form a search space for the parameter to compute the number of rotation. For example, the MVM of 4096, there are 32 different combination strategies. We can find the best strategy with small rotation. Now we turn to the convolution. Can we represent the convolution with the metal kernel? The widely used convolution is email to core, but email to core transforms the input. The input is ciphertext. It's hard to recognize in FHE. So we shift. An interesting observation is each row of the I column is the rotation of input in the CHW layout. This is a very important observation. The true power is we can transform the convolution into Imler pattern. So we, instead of transform input, we transform filter and use rotation to get input. The true power of kernel to column is that it allows us to compute the convolution using the same Imler pattern. For the large convolution, we first partition into small a group of small convolution, and each small convolution is use emerald pattern. So how do we bring all these ideas together? The metal kernel design first transform MVM and convolution into initial emerald pattern, and then emerald optimization is applied by horizontal and vertical batching. Here is the emerald optimization, which the input is an initial emerald pattern, and batching strategy by vertical and horizontal, driving the data patching of B, and the output is an optimal emerald pattern, less rotation and optimal slow utilization. We evaluate the metal kernel in the ANT-AC FHG compiler and compare it with the FHG leap in kernel level, model level, and compile time level. The question one: can metal kernel outperform FHG leap across with different size of MVM and convolution? And the question two is: can metal kernel outperform FHG leap across DM model? We evaluate many AI model with small input of CIFAR. The image can fit into the size of a ciphertext, and the ImageNet, which cannot fit in a ciphertext. So we need to split the input into different ciphertexts. The FHG leap cannot compile the large model. Here is the compile time. Most compile time is spent on the transformation of matrix B and the filter in the convolution. Here is the conclusion. Metal kernel provides an abstraction between the kernel and the CKK primitive, and the abstraction provides a good cost model for the number of rotation and the slot utilization. It can unify the MVM and convolution. There are still other work we need to abstract with the metal kernel. For example, the attention kernel. Both the input of attention kernel are ciphertext. It's hard to organize the ciphertext. For the large models, such as transformer, the parameter is penned by 10 of 100 times. So we need to model partition and efficient ciphertext communication between the CPU or GPUs. Thank you for your attention.
If not yet, then I do have a question. So I noticed that you're from a company called Ant Group, right? So I was wondering whether your approach has been applied in the company or is in the industrial practice. Is it just research, or has it been actually used in the company?
Currently, it is a research, but it is also put in the production.
Okay, thanks. Speaker is Anand Kabaha from Technion. He's going to talk about quantization.
Hey, I'm Anand, and today we are going to talk about quantization with guaranteed floating point neural network classifications. So neural networks are very powerful, but they require high computational complexity, significant power consumption, and large memory allocations. And because of that, it's hard to deploy them on resource-constrained devices, for example, mobile phones, smartwatches, or real-time applications. So a popular way to reduce the computational complexity of neural networks is to use quantization. And in quantization, we reduce the precision of weights and activations from floating point to a lower bit format. For example, int 4, int 8. Now, two approaches to apply a quantization is PTQ, post-training quantization, and the quad, quantization-aware training. In PTQ, we have a training set. We train the network. After the training, we do the quantization. In quad, we consider the quantization error in the training itself. So the resulted quantized network is more robust to quantization error. Now, both approaches are successful, but they do not guarantee floating point consistency. Means the quantized network is not guaranteed to act like the floating point network. And this brings us to our goal. We want to design an approach to guarantee classification consistency between a quantized network and its floating point counterpart. Now, to understand this, let's consider these two classifiers. We have floating point here and 4-bit, its counterpart 4-bit quantized classifier there. We feed two inputs, the blue and the green ones. At the output of the floating point, we have classification to C1. At the output of the quantized network, we see that the blue changed classification to C0, and the green stays at C1. Now, we call the blue input inconsistent because it changed classification, and the green, we call it consistent because it remains the same. Now, if we want to guarantee that the quantized network always classify like the floating point network, we need to find all the blue dots, capture them, and fix them. So the question now, can we identify all classification inconsistencies? And our goal is to detect all the inputs that now classifies differently between the floating point and the quantized network. And here we show two impractical approaches. First, you can say that we can go for all the inputs, do the tests, push them into the two networks, and store the results in some big database. Now, this approach is impractical because in neural networks, the input domain is huge, it's continuous, so we cannot do that. The second approach, also impractical, is to do that in real time. Each time we have an input, we push them into the classifier floating point and the quantized, and check the output if they classify similarly. Now, this is also impractical because if we can do that in real time, then we do not need the quantized network. We can run only the floating point network. So what requirements we want from our approach? First, we wanted to work at inference time only on the quantized network. It's important. Second, we wanted to provide a guarantee for any input to certify it as consistent and or flag it as inconsistent. And this brings us to our main idea, the QIF bound. Now, to understand this bound, let's consider again two classifiers, floating point and quantized, accepts a 2D input and classify into C0 and C1. Now, if we look at the classification results, we can see that for most of the cases, for most of the inputs, they classify similarly. So they're consistent. But around the decision boundaries, in this red region, we have all the differently classified inputs. So our goal now to define a bound, starting from the decision boundaries of the quantized network, expand until it covers all the red region. That's our goal. Okay, so we said that we want to capture distance from the decision boundaries, and how we do that? We depend on a common term which is called classification confidence. Now, in classification, we typically have an input. We show it to the classifier, and at the output, we have classification scores. Now, classification confidence is defined as the maximal score of class C minus the score of class C minus the maximal score of the rest labels, rest classes. And to visualize this, let's consider this figure. At axis Z, I show the classification confidence. At axis X and Y, we show the input domain. Now, we can see that at the decision boundaries, the classification confidence is 0 because we do not classify there. And it expands, it goes higher when we go away from the decision boundaries. And this also happens in the quantized network. Now, as I said, our goal is to define a bound starting from the decision boundary of the quantized network, means start from classification confidence 0 and expand until we cover all the differently classified inputs. Okay, so let's see how now we define our property using the classification confidence. We say that the QIF bound is the maximal classification confidence such that the quantized network classify to C and the floating point network classify otherwise. This means we want to find the input with the maximal confidence such that it classifies differently. If we find that, we can bound all the differently classified inputs. Okay, after we found this bound, at inference time, each time we have an input, we can compute, run it into the quantized network, compute its classification confidence, and compare to D. If it's larger than D, then it's in the gray region. If it's smaller than D, then it's in the red region. Okay, so we said how we showed how we define our probability, and now let's see how we compute it. To compute it, we use MILP, mixed integer linear programming, and we have two constraints: the classification confidence of the quantized network and the classification confidence of the floating point network. Now, to encode the floating point network, we need to assign one Boolean per neuron in the network because we have one nonlinearity at the 0. But to encode a neuron in the quantized network, we need to assign B plus 2 Booleans, which is a huge number. Especially that the MILP complexity is exponential in the number of Boolean variables in our property. And how we deal with that? We use linear relaxations. We try to reduce the number of Booleans using linear relaxations, and we have here 3 ideas. For example, clipped parallelogram, and trapezoid. Here we just replace the nonlinearities using linear relaxations. Another idea is to use relations. Remember that we have 2 networks, the quantized network and the floating point network. We can add linear constraints to tie and encode relations between the optimization parameters of the 2 networks. We just compute the differences, propagate these differences, and turn them into linear constraints. After that, we encode that into the solver. So the solver can use this data to converge to an optimal solution quickly. OK, so now let's describe our system. We call our system compact. It runs in 2 stages. First stage, we run it once offline to compute the bound, and the second stage is inference. When we have the bound, we can run now in real time and check consistency. So our approach our system accepts as an input floating point, a quantized network, and class C. We first MILP encoding, then add the linear relaxation, then add the relations, and then push all the encoding to the MILP solver. At the output, we have our bound. From that, each time we have an input, we can run it into the quantized network, compare its classification confidence to the bound, and apply a correction mechanism if we need to do the correction mechanism. The correction mechanism is only applied if we are in the red region, what I showed previously. OK, so now let's describe one of our correction mechanisms. In our paper, we provide 2 correction mechanisms, APR, adaptive precision refinement, and the QF ensemble. And here I will explain the APR. In APR, we assume that we have a floating point and several quantized networks, for example, int4, int8, int16. Each time we have an input, we push it into the quantized network with the lowest precision. If we manage to guarantee consistency, then we finished. Otherwise, we pick higher precision. If all the quantized network failed, we fall back to the floating point network. Thus, the APR is guaranteed to always reproduce a floating point decision. OK, so now let's talk about our evaluation setup. We evaluate compact on several data sets, on fully connected and convolutional networks. We use PTQ and QUAT as baselines, and we use matrix multiplication cost and effective bit precision as evaluation matrices. Now, to understand this evaluation matrices, let's consider this example. We have here 2 quantized networks, int8 and int16. The multiplication cost of int8 is 8 by 8, and the precision is 8, of course. The multiplication cost of int16 is 16 by 16, and the precision bit is the bit precision is 16. Now assume that we want to run now APR. Say we first run the int8 network and failed. After that, we continue to the int16 int16 network and manage. Now the total cost is 8 by 8 plus 16 by 16. And the effective bit precision is the square root of this multiplication total cost. Now, in this example, we can see that we produce a floating point classification result. And while we reduce the multiplication complexity compared to floating point by approximately 2x, which is the real strength of our approach. We can create floating point classification without running floating point. OK. So here we show the APR performance. We can see that it obtains 100% consistency with floating point and reduced its computational complexity by 3.8. The baselines cannot guarantee a perfect consistency, but they have lower costs compared to compact, which can get to 1.4 times. And here we show a case study over a system of airplane collision avoidance. We run a cast-XOR simulation. In this simulation, we have two airplanes, O and I. O have a neural network in it to try navigation. And all the idea is to navigate to avoid collision with airplane I. Now we run this over 10,000 simulation, and we can see that compact reduces the floating point computational complexity by 6.25 times with average bit precision of 9.76. The path differences, if we measure the path differences of compact and compare it to floating point network, we can see that we have 0 feet difference. And if we look at other networks, for example, other quantized network, for example, Int16, Int12, Int8, we can see several thousands of difference in the path. Again, we can reproduce floating point results with a significant smaller multiplication cost. Okay, so now let's summarize. We address the problem of classification inconsistencies after quantization. We introduce our new concept, the quiff bound. We propose compact to compute the quiff bound and mitigates different classifications between floating point network and quantized network. Our system employs MEAL, novel linear relaxations, and relations to reduce the complexity of our problem. We propose two correction mechanisms, APR and the quiff ensemble. And we can see that we can reproduce floating point performance by reducing the multiplication cost significantly. Okay, thank you for your attention and the questions.
Please go to this.
My understanding is you don't change the quantization method and use the high precision network result to create the low precision network. The correction in the page 8.
Here? The correction here?
8.
8?
8.
Okay.
Sorry, I forgot. Each different input have different correction parameter, right?
No, for each input we can get one correction depend on the mechanism of the correction. For each input, either we correct it or we do not need to correct it. But in the two cases, we are guaranteed to have a floating point classification. Say you can be here in the gray region, run floating point of run quantized network of Int4 and get a floating point result. You don't need to run floating point after that. You get the floating point result without running the floating point. But it's proved, it's guaranteed.
It's a great talk and a significant result. I just wonder how well it scales. Does it scale for every benchmark in VNN comp, for
Scaling
example?
is an issue, especially when we're talking about formal verification. We can scale to small neural networks, which can get to several hundreds to several thousands of neurons. But a lot of work for scaling is waiting for us, I think.
All right, thank you.
Scale is an issue. Okay, so thank you.
Session is Jaeyoung Won from MIT. He's going to talk about the continuous tensor abstraction.
Okay. Hi, everyone. Can you hear the mic? Okay. I'm Jaeyoung, and today I'll be talking about our work on the continuous tensor abstraction, where you can access tensor with real numbers. So arrays, which today also tend to be called as tensors, are one of the most universal ideas in computing. We all learned them in our very first programming class, and they show up everywhere, like from scientific simulations to deep learning. And whether it's old languages like Fortran or modern frameworks like PyTorch, they all share the same basic tensor abstraction. And since every tensor lives in integer grid, and this property allows compilers to be really powerful, like they can do loop transformations and auto-vectorization, auto-parallelization, and all the polyhedral tricks. So as programmers, we can just write something very simple, like an INSUM, and the compiler can turn this into very fast code that you can run on the hardware. But there's a whole class of applications where these compiler optimizations just don't work. Things like point cloud processing or spatial databases. So these communities have to build their own framework and fragmented libraries built on top of different data structures. So we ask ourselves, like, what makes them different? So one thing we found was these data have coordinates that are real number, not integer. Let's look at convolution as an example. If your data lives on integer grid, you can write convolution in a clean INSUM-like form, and the traditional compiler turns that into very fast code. No problem here. Now let's try the exact same convolution, but this time the points don't sit on the integer grid, but they can be anywhere in real number space. And this is what people call as point cloud. And if you want to write a very high performant kernel for this point cloud convolution, in practice you probably have to write like 3,000 lines of code in C++ or PyTorch. Unlike traditional tensors, you now have to decide how to store this data in real memory and how to access those data structures very efficiently on the hardware. And the problem is, none of the existing high-level tensor language compiler can help you here. But here's the key idea. What if tensors could have real value coordinates? Then you can index them with real index and still write the exact same INSUM as before for the point cloud convolution. And now imagine if there's a magical compiler that can take this real index INSUM and generate efficient code automatically for you, then the user can now write the same simple high-level tensor expression as before, nothing new to learn, but under the hood, everything works for the real coordinates. This is exactly what we are doing in this work, and we call such model as continuous tensor abstraction. From now, I'll explain a continuous tensor and the language we use to express computations, which is INSUM. And then I'll walk through how we can compile these INSUMs into efficient code, and finally show some evaluation results. Let's first talk about what we mean by continuous tensor. Previously, when people talk about tensor, we usually imagine something like integer grid, like pixels. But what if we remove this grid? Now your data no longer has to sit on integer grid, but can live at any real number domain. So you can think this tensor as mapping from real to value domain. So in this figure, in this particular figure, any x, y coordinate that falls on the blue pinpoints has some value. Otherwise, the white regions represent 0 value. Of course, if we go all the way to like full generality, things can be really messy. So you could have tensors like this divided by really irregular and complex boundaries. And when we try to multiply these two tensors, we have to find where those boundaries actually intersect. So this can lead us to like root finding problems and handling all sorts of numerical edge cases, not something we want to wrestle with. So in this work, we take a more structured approach. It's still continuous, but designed to be much more practical. So we focus on piecewise constant tensor. And the nice thing is the many applications I mentioned earlier can perfectly fit within this model. So when we say about piecewise constant tensor, first, it is consisted of finite number of pieces. And each piece holds a constant value and is an axis-aligned box with any real number boundaries. And the entire pieces cover entire region without overlapping each other. And the fun thing is, even with the structure, we found that we can still do a lot of interesting things. Starting from the previous example, you can represent boxes by assigning non-zeros to the interested box, like piece 1 and piece 4 here, and zeros elsewhere. You can do lines similarly, and of course the point clouds as well. And now let's talk about the language we use to describe computations on these continuous tensors. We extend the familiar Einstein notation, except now the indices in Einstein can be real, not just integers. So for example, I prepare here element-wise multiply between two continuous vector. This looks exactly same as the standard Einstein, ax times bx. The only difference is that the index x is now a real variable. And you can also do a multi-dimensional broadcasting element-wise multiply like axy times bx directly on 2D continuous tensors again. And one important difference between traditional Einstein and continuous Einstein is that how reduction works on continuous domain. So let's say we have 3 non-zero points in a continuous vector like this, and we just want to sum them up. And in order to do that, we simply add their values together, just like in discrete case. On the other hand, let's say if our user has a 1D continuous vector, but now with an interval. So value is 3 across the range from 0.9 to 1.8. And if the user wants to multiply this value 3 with its interval length, this means integral. So in our language, we need to distinguish between these two reduction modes, summation versus integration, depending on what the user actually needs. So in our Einstein, we designed to let the user explicitly specify which measures to use for each reduction variable. So if you want summation, user should mark that variable with the counting measure mu sharp. And if you want integration, you mark it with a Lebesgue measure mu lambda. So in other words, you can think the measure acts like a signal, tells the compiler how to reduce along that axis. In general, our continuous Einstein language takes following form. The notable difference, again, shown in blue, the user specifies a measure for each reduction index. And on the middle expression, the main expression can include tensor access with affine indexing and a variety of arithmetic operations. Now let's move on to how we implement continuous Einstein efficiently on the real hardware. And because our tensors are piecewise constant, we can specialize the implementation using this property. So let's walk through an element-wise multiply example again. The first step for the implementation is to partition the iteration space into regions where both tensors A and B are constant. So you can see in the middle, the space is now partitioned into 6 regions, each formed by the intersection of pieces A and B. Next, for each partition, we evaluate the Einstein expression. So since both tensors are now constant in that region after the partitioning, all we need to do is just compute that expression with constant values. And here I prepare the pseudocode of the implementation for this Einstein to partition the iteration space. We can check all pairs of pieces from A and B and find their intersection. And then we evaluate the constant expression for each partition. And this all pairwise comparison works really well to figure out the partition, but this can be really expensive, quadratic in number of pieces. So one key optimization is that we don't actually need to compare all of these pieces. Instead, we can partition the iteration space much more efficiently. So we can use a 2-finger merge technique. By walking through the pieces in sorted order, we can avoid unnecessary comparison, and algorithm now becomes linear. And what we found was, in reality, a lot of piecewise tensors have a large amount of 0 pieces. So by skipping those with a sparse intersection approach, we can avoid doing wasted more further. And now this makes the complexity depend only on the number of non-zero pieces instead of the full sizes. So to summarize, we extend Finch, which Willow introduced earlier in this session, and to a compiler that can take arbitrary continuous INSUM expressions and generate very efficient kernels. And if you're curious about how the memory layout for the multi-dimensional piecewise constant and how we extend Finch and how we handle continuous reduction, please see the details in the paper. And now let's move on to the evaluation. We will start by showing you one of our applications, a radius search query. This is simply asking, given a circle query, which points lie inside the circle. And we formulate this problem as an element-wise multiplication between two-dimensional tensor. The point cloud tensor points x comma y, and the box tensor box x comma y. And each blue points in the red box carry value 1, while the other white regions are 0 valued. So as a first step, we first place the bounding box of the circle in the red box into the piecewise tensor representation. And then we apply a mask using a circle condition. So this condition acts like a filter, so only the points inside the circle will eventually remain. And then we compare our generated kernel of that INSUM with Shapely, a state-of-the-art geometric library. And we see that we got like huge speed up compared to the Shapely. This was mainly because Shapely is optimized for box queries. So for the circles, they also have to materialize all the candidate points within the bounding box, similar to what we did, and then filters them in the second pass. In contrast, our compiler fuses everything into a single pass, so avoiding unnecessary materialization. What's so powerful here is that our model can naturally express many applications that are very hard to write in simply in traditional tensor languages. So from geometry queries like radius search query or box search query to interval joins and all the point cloud convolution, each of these can be written in continuous INSUM very concisely with just 1 or 2 INSUMs. And across a lot of applications, our compiler can achieve comparable or better performance than handwritten libraries while reducing programming effort a lot. So when you look at the point cloud convolution case, we found out we can save up to 100x fewer lines of code with better speed. And I want to conclude with this slide. And tensors and geometry, two worlds rarely talk to each other previously, but we believe this work can act as a bridge so that even non-tensor world programs can be explained in tensor terms. So we introduced INSUM concepts and sparse tensor optimization concepts to the non-tensor world. And we believe different direction can also be a very interesting future work. So can we leverage ray tracing core in modern GPU or spatial data structures like bounding volume hierarchies for tensor computations? And I hoped you enjoyed the talk and happy to take any questions.
Hi, nice talk. I have one question. Given that you use constant values to do the tensor computation, is there any trade-off? I mean, between the performance and, for example, precision or?
You mean the piecewise constant tensor only?
Yeah, right.
Yeah, that's one of our design choice because when we, let's say, that's for the performance trade-off because we could have the value to be more complex arbitrary function using symbolic engine, but that can take the performance really bad in some cases. So we want to keep the simplest possible. So we only store the scalar value. And in most cases, we can represent many applications, even with piecewise constant. Okay. But that's our future work.
Okay, thank you.
Hi, great talk. I see that you extended INSUM notation with affine operations for convolution, and that's very cool. Have you considered other extensions, or would it even make sense, like tensor concatenation?
Oh, we can think about concatenation between, we can think about continuous support for the concatenation.
Like a sum of 2 point clouds, in a set theoretic sum of 2 point clouds.
Yeah, since concatenation can be represented as a affine index, and I believe Finch can already support concatenation. So we haven't tested it, but I think we can already support concatenation since we can support affine index.
Thank you.
Yeah.
Okay, for the sake of time, we have to stop the session now. If you have any other questions, please find the speakers afterwards. Thank you.
Very easy, yeah. Today is really good.
Yeah.
So do we need to close it?
Oh, you can leave it on. It's okay.
It's okay,
It'll
just
just
put
change
it here.
batteries tomorrow.
Okay, okay.
Yeah, bye.